Yes, ma'am. The webinar is now live, ma'am.
Good afternoon to one and all present here. We are on the last but one day evening session. We have with us two plenary sessions today, followed by three parallel sessions, one in fuzzy math and applications, one in physics, and the other in paper presentations. For the first plenary session for the evening is Professor Hiroshi Sakai from the Department of Basic Sciences, Faculty of Engineering, Kyushu Institute of Technology, Kitakyushu, Japan. Professor Hiroshi Sakai received his BS and MS and DS degrees in mathematics and computer science
Ma'am,
from Kyushu.
sorry to disturb you, ma'am. Are you starting the session, ma'am?
Yeah.
Ma'am, it's supposed to start by 4 o'clock.
Oh, I see. I thought it is 3:30.
Yeah.
No.
Okay, we'll wait.
Yes,
Okay, ma'am.
yes. Thank you.
A very good evening to one and all present here. We are on the last but one day afternoon session. We have three plenary speakers. The first speaker is Professor Hiroshi Sakai. The second one is Professor Rajkumar Verma from Chile. And the third one is Professor Vishwanath Ramakrishna from Dallas, USA.
I'm
The,
Hiroshi Sakai. Can I start now?
just a minute, sir. I will just take 1 minute to introduce you to the
Thank you.
people. Good evening to Professor Masahiro, who has joined us today for the session. Professor Hiroshi Sakai is from the Department of Basic Sciences, Faculty of Engineering, Kyushu Institute of Technology, Kitakyushu, Japan. He received BS, MS, and DS degrees in mathematics and computer science from Kyushu University, Japan. Currently, he is a professor of the Department of Basic Sciences at Kyushu Institute of Technology, Kitakyushu, Japan. He is serving as an advisory board member in the International Rough Set Theory Society and an editorial board member of several journals. His primary research interests include rough sets, mathematical logic, soft computing, logic programming, and data mining. He is a PC member of several international scientific conference series. He has published over 100 research articles for books, journals, and conference proceedings. His areas of interest are statistical science, intelligent informatics, rough sets, computational mathematics, logic program. His research career runs through soft set theory and its applications, rough set theory and its applications, rough sets, computational mathematics. He runs a project from 2005 till date. Data mining from incomplete information systems, incomplete information data mining project running from 2010 till date. He has received several honors and awards. To name a few: outstanding contribution in reviewing 2017 Japan, excellent paper award Japan 2016, senior membership Japan 2015, excellent paper award in FIM 2013 conference Japan. We are indeed glad to have such a distinguished plenary speaker for the day. Over to Professor Sakai.
Thank you, Professor Kennedy. Yes, I link my page. Yes. Yes. Can you see
Yes,
the
sir.
PPT? Yes.
Yes,
Thank
sir.
you. I'm Hiroshi Sakai in Japan. I'm very glad to have this presentation. The title is a consideration about rough sets, the a priori algorithm, ensemble learning, and the rule-based functionality for explainable AI. This presentation is a survey of this presentation surveys the environment of our systems toward realizing the functionality of the explainable AI. At first, I would like to thank the organizers of FIM 2020, and I should be grateful to President Professor Watada, who always encourages me in Japan. And the chair, Professor Kennedy, invited me to this presentation. And this research is supported by the JSPS grant. In this presentation, we consider the next issues. The black box problem for neural network-based AI, namely, conclusion is obtained, but reasoning is unclear in such AI system. To complement the black box problem, we reconsider the functionality of the rule-based decision making. Actually, we are coping with this issue, and I will talk about the current background and the perfect perspective. I downloaded this sheet from the Google Cloud web page. We can see the necessity of considering the explainable functionality in AI. And Google's explainable AI sheds light on how machine learning models make decisions. Uh, we also see similar projects from other IT companies' side. A solution to the black box problem is a very significant issue now. The recent AI responds the decision, but the process and the reasoning of the decision is not clear. And this is a chart of the rule-based functionality for the explainable AI. We have coped with rule-based generation, rule generation from big data, and incomplete data, and heterogeneous data, etc. For queries and conditions, we employ the obtained rules and have decisions. For query and we employ the association rules and have decision plus reasoning. The used rule is an evidence of reasoning. This strategy is known as rule-based decision making. We show the environment toward realizing this functionality. This is a content in this presentation. At first, I describe rule generation examples from the car evaluation dataset, and the congressional voting dataset. Then we discuss decision making from the suspicious dataset and the lithology dataset. DIS means a standard table, and NIS means a table with non-deterministic information. NIS means tables, rule generation from tables with uncertainty. In NIS, we follow the possible world semantics, and we characterize the certainty and the possibility of rules. At first, we go to the car evaluation dataset. This dataset deals with the evaluation of the used car. The dataset consists of 28 objects and 6 attributes. 6 attributes. The decision attribute is acceptability. There is no missing value. And I change the sheet. Yes, this is the part of the car evaluation data set. Here is object and here is attribute, and the decision attribute is acceptability. And this data consists of 1728 objects. And in this, from this table, we want to obtain characteristic implication, which is termed as rule. And we execute our program, and in 0.91 sec, we have these files. The rule is stored in this file, in these files. And this is an example. An example of rules. And I explained the orange blocked rule. This implication, this is a condition and this is a decision. If attribute 1 is high, implies acceptability is arc. This implication occurs 0.188, namely 18.8% of 1728 objects. And if attribute 1 is high, implies high, we can conclude acceptability unlock with 75%. And in order to have rule, we specify this support value and accuracy value. And the system generate rules, generate implications satisfying more than support and more than accuracy. Such implication is generated from the tables, and we see such implications rules. In this case, support is 0 and accuracy is 0.9. So implication satisfying such condition is generated. And this is a implication with 3 condition part. And this is an implication with 4 condition parts. Like this, we can generate rules from the car evaluation data set. I'm sorry. Yes. Now we go to the congressional voting data set. Congressional voting data set. This data set consists of 435 objects and 17 attributes. And the decision attribute is a Democrat or Republic. This data is a voting data set in US Congress. And there are 392 missing values. I change page. Yes. This is a part of the congressional voting data set, Republic or Democrat like this. And here is question. Question means missing values. So we replace either yes or no to this question. Then we have one table, and but such table uh, occurs. This is two cases, and there are 322 missing values. So the possible table occurs 2 power 392. This is almost 10 power 120, more than 10 power 100 possible tables. And we want to handle implication which surely holds and which possibly hold. Uh, and so certainty is defined uh, implication which satisfies, this is a condition, no rule, and in each of 10 power 100 tables. In every table, an implication satisfies the condition of the rule. We see this implication is a certain rule. Certain rule. These are the obtained certain rules. Certainty. Every implication is a rule in each of 10 power 100 possible tables. And this is a obtained rule. Every implication is a rule at least one of 10 power 100 possible tables. For more detail, please see some papers. We cannot enumerate 10 power 100 possible tables. We only examine the maximum table and the minimum table, two tables, and we can calculate these rules. I change the, yes, and now we go to the rule generation and decision making from the suspicious data set, and the similar condition, and this is a data. This is a data of the suspicious data set, very complicated. And we want to generate rules. The support is more than 0.001 and accuracy is more than 0.5. And our system generated 997 minimal rules with notified 0 and 22 rules with notified 1 rules. Like this. Dispute CD3 implies notified 0. And this is a obtained rule, and this is support, and this is accuracy, the rule number. And this is a part of the generated rule with 3 conditions. This is a obtained rule, and support, accuracy, and the rule number. Like this, we can generate rules from tables, and we are now prepared this association rules. So we apply this association rules for decision making and with reasoning. The reasoning process is very simple. For condition P1 and P2, if there is a rule P1 and P2 implies Q, then we have a decision Q. And this decision is supported by the reasoning P1 and P2 implies Q. Based on this rule, the decision is concluded. It's the decision process is very clear, and the reasoning is very clear. we think this is a functionality for the explainable AI. And actually, we applied the program and for 20,000 objects, we applied our rule, and this is a case of the for object 19988 object. We employed 50 first rules and 1006 rules and 1008 rules, because these rules, the maximum lift value was maximum. I employed another criterion lift, and the lift value is maximum. So we employed 50 first implication and 1006 implication rule and 1008 rules. The 1006 rule is like this, very complicated, but and so based on these rules, the notified one is concluded. Notified one is concluded because 8.66 is much bigger than the 1.02. And as for evaluation, threefold cross validation was performed on the training data, and the average estimation rate was 94% for this estimation. The case for rule generation and decision making from the Research data set. And for the detail is, I will omit the detail. And this is a data. This is a data. Like, and they are missing values. They are missing values. And we translate. This is a continuous values. So we discretized based on this strategy, this interval, and generated non-deterministic information system. And this is a obtained rule with 3 condition part like this. And we estimated 570 object attribute value. And we applied 21st rule. 21st rule. This is a 21st rule. And we applied and 1.33 is a maximum lift value. Maximum lift value. So we can employ one of 3 rules, but and we conclude the system concluded Research 4. Research 4, but the estimation was wrong. Actual value was different. Yes, and for this, in this case, the threefold cross validation was performed on the training data, and the average accuracy was 85%. And this is a conclusion.
Professor Sakai, can you refresh yourself?
Is it time?
You have another 5 more minutes.
5 minutes? Yes, okay. To complement the black box problem in neural network based AI, reasoning, rule-based decision making will be necessary. These are the related papers. And we are now developing the environment 1 and 2. We are now developing the environment of rule generation and decision making based on this chart. Yeah, I have already coped with this part, but not only rule generation, but we need to apply the obtained rules to decision making. This decision making is not new concept. Formerly, rule-based system, rule-based reasoning was employed several times, but recently we could handle several different types of rules from several different data sets. So we can apply the obtained rules to decision making, not only decision,
Excuse me,
but also decision plus reasoning. Yeah,
Professor, your screen is not
I close my presentation. Thank you. Yes. I'm sorry. Yes. Yes, I close my presentation. Thank you. Okay.
Thank you, Professor Sakai. Participants, anybody has any questions, queries, or comments to make? Professor made an elaborate research problem on rule-based functionality for explainable artificial intelligence. Rule generation with two examples he showed us, and decision making again with two examples, and how to generate the rule base using machine language, implications, certainty and possibility values, and how to handle huge data. And even seeing the maximum and minimum data makes us go makes our head go reeling. So I'm just wondering how big it would be to see the entire data, and the system generated rules working out very efficiently. Thank you, Professor, for such an elaborate and crystal clear presentation. Thank
Professor,
you
there
very
is a
much.
question
Thank
for
you.
you from the
Okay,
audience. I will read out the question.
is on the chat.
Yeah. A lot of security involves one vendor solutions. But as we look at future designs, there are more multi-vendor heterogeneous designs. Each one of those potentially has a different level of security. How do we build that into the architecture so there isn't a problem?
Mm, mhm, mm. I'm sorry, but I'm not consider the security. Uh, in my framework, I generate rules from several different types of dataset, and such data. I want to apply these obtained rules to decision making, but I'm not open the such system to the we only consider such system. So currently there is no problem for security. I think the security problem is another problem. In my framework to generate rule and apply the rule to decision making. If the system is implemented completely, we may open the system, but the security problem is after opening the our system. Is it okay? Security, I think security is not related to my work.
Yeah. Can I add on, Professor? He has a saying with respect to artificial intelligence, how to handle huge data systems. So if you have to speak about security, then you have to, that's a different work, that you have to bring in the security into the database systems. Then maybe you can think of how to handle such database systems. Actually, whatever Professor spoke today is not connected to this area at all. Am I correct, Professor?
Yeah. And I'm not familiar with the security program and security environment. I can understand, I can know the mathematical cryptography and the RSA cryptography, but the actual environment of the security, I'm not familiar with. Thank you.
Thank you. Thank you very much, Professor. The second speaker for today is Professor Rajkumar Verma. Is Professor Rajkumar Verma there?
Professor's not a join, ma'am.
Oh, I sent a reminder also. The third speaker for the day is Professor Vishwanath Ramakrishna.
I'm here. I'm here.
Just a moment, sir. Somebody's calling. I'll just check if it is he. Hello? Actually, he's not available. And also, Professor Vetrivel has issues with his internet connectivity. As you would have read in the papers, Professor Ramakrishna, that there was a cyclone that hit in the neighborhood of Chennai, and a lot of problems have occurred in certain places, not everywhere. We are very safe here in Stella Maris running the show. But
Okay.
what actually happened is IIT has lost all the internet connectivity, and their email system is totally lost. So
That brings back reminders of when I was a student at IIT Madras. We had to do all those computing assignments on those punch card machines. And every time there used to be a cyclone to ruin things. Okay. Let me know whenever you're ready. I'm ready to start my talk.
If you are ready, I think I will introduce you and I will
Sure.
invite you to be part of the
Okay.
session.
Mhm.
Uh, can my video be on, Dana?
Yes, ma'am. Ma'am, you can turn on your video, ma'am.
It says you are unable to start the video.
Yes.
Okay.
I can see you now.
Yeah. Professor Vishwanath Ramakrishna, we are very proud of you. He is
Thank
an
you.
IITian from Madras IIT, Department of Mathematics, 1986 batch. He did his BSc honors from St. Stephen's University of Delhi, and then moved on to Washington University, where he did his MS and PhD. And he is professor in the University of Texas at Dallas since 2005. His research areas are very vast and very impressive. And he has done several projects actually, and the number of publications, I don't know, it goes numbered down the list. But we are very proud of you because your mother was Stella Marian. His mother passed out of the economics department in 1963. She wrote to me the other day, and I have passed on the information to the economics department. So, in my inauguration, I did say, Professor, there is a lot of push for professors to come and speak in this conference, especially when it is Stella Maris, because they have some relation with Stella Maris. And as I said that, Professor Venkat Subramaniam, he said his niece is from here. Yesterday, another professor said his wife is from here. So it gives a lot of good feeling for Stellamarians to have so many of their alumni in uh, excellent positions and bringing up children, nieces, nephews, in-laws in a very good connective level. So over to Professor Vishwanath Ramakrishna.
Okay, I'm going to try and share my screen. The other day I had problems, but hopefully today I won't. I have the able assistance of one of my best students right next to me. So, and of course, maintaining social distance. So let me try, okay? Give me a second,
Okay,
please.
sir. Yeah, and sure, sir.
This one, right? Can you see my screen now?
Yes, sir. Yes, sir.
All
Very
right,
clear.
as Dr. Kennedy mentioned, this conference is of great importance to me. This is my first FIM conference. I wish I could be there in Chennai in spite of the cyclone, because it's a city I remember very fondly. My mother graduated, as she said, in the early 60s with a BA honors in economics. My father went to Loyola College, also in economics. I went to IIT Madras. I think it's still called IIT Madras, correct?
IIT Madras, Chennai.
Yes, and I have great memories of the faculty there. Dr. P.V. Subramaniam, who's one of the organizers, taught me real analysis. Dr. Kulkarni taught me analysis as well. Dr. K. Swaminathan was a mentor for me. I have very fond memories, and without their help, I don't think I'd be where I am today, because I switched from physics to mathematics. All the epsilons and the deltas hit me very hard in the first few months, but I somehow survived. So I wish I was there, but this is the best we can do. And I have to extend first a vote of thanks to Dr. PVS for introducing me to FIM, and then to Dr. Kennedy and her collaborators in organizing this wonderful conference. So even though it's terribly early in the morning, I'm so happy to be here. So as you can see, this work is joint with one of my best students, Emily Herzig. She's at Texas Christian University. And of course, as I said, I have the able assistance of one of my equally good students, Mr. Abu Halal, who will defend his thesis in about 4 days, right? Correct, Monday?
Yes.
All right. So what I'm going to talk about are axis angle representations for higher orthogonal groups or higher rotations. So let me begin here. I'll do this, right? One second. One second. Let me. Yeah, here it is. So let me begin by discussing generalities and remind you how it is done in the SO3 case. That is three-dimensional rotations. And I'll tell you what ought to be the higher dimension generalization. Of course, explicit formulae are not possible unless we stick to slightly lower dimensions. So I'll fully illustrate the case of SO5, and hopefully that will give you a picture of what is involved, okay? So preliminaries. So I remind you, the special orthogonal group consists of real matrices n by n whose inverse is their transpose, and in addition, they have determinant 1. So these rotation groups are very important. Certainly, n equal to 3 is the most important. Direct products of SO3 sitting as subgroups of the higher dimensional rotations are very important. They arise in robotics, animations, switched electrical networks. If you give me any matrix in SONR, I can write you a circuit consisting of inductors, capacitors, and resistors, an ideal circuit, sort of lossless, whose dynamics will be described by that matrix. Of course, you can say those applications are a bit contrived because nowadays people are talking about the smart grid. I don't know how important that will be there. But then for purely mathematical reasons, and you have neural networks, recurrent neural networks, where it's been promoted, orthogonal matrices have been promoted to avoid the so-called gradient explosion problem. So succinctly, these groups are very important, and therefore their study behooves our attention. Okay. So when n is odd, if this n is odd, 1 is always an eigenvalue. And we call any normalized eigenvector its axis. Strictly speaking, that terminology is justified when the multiplicity of this eigenvalue 1 is exactly 1, but we'll still, to avoid circumlocution, continue to use the word axis, okay? All right, so now SO3 case, I'm gonna go into, so what happened here? So, okay, so what will happen is, so once you find this eigenvalue in dimension 3, in the plane perpendicular to that axis, right? Your rotation is, your matrix is performing a two-dimensional rotation, a counterclockwise rotation. And that is the so-called angle of the rotation. Good, is this, I hope this is clear so far. And that justifies the terminology axis angle. And in other words, to specify the matrix, it's good enough to specify the axis. That's two parameters, three components of the vector, but normalized, and then one angle. So it matches the dimension, okay? All right, so how do you find, so there are many ways to find this axis angle representation. I'm going to suggest a pedestrian way, and then I'll give you a different way. So first and foremost, it's easy to find the eigenvalues of such a matrix. So you don't really have to solve a cubic equation. One is guaranteed to be an eigenvalue, so you divide the characteristic polynomial by x minus 1, and you have a quadratic. And then some elementary thinking along the lines of Cayley Hamilton will tell you any non-zero column of this matrix that alpha square plus a square plus alpha square identity is going to be a axis, and you can normalize that, okay? So that will give you the axis. Right, and then to find the angle, of course, is the eigenvalue. So is some e to the I theta, the corresponding theta is the angle. But there is a better way, in my opinion, to find the axis angle representation. And in fact, this is the way it is done in practice as well. And this is through the well-known connection between rotations, three-dimensional rotations, and quaternions. So quaternions are some sort of, the initial purpose was to generalize the complex numbers, but they have found a life of their own, which goes far beyond they're being able to generalize complex numbers. So, quaternion has a real part and three imaginary parts. You choose a unit quaternion, let it, that is, you normalize its length, and let X be a quaternion with zero real part, so purely imaginary. Then X going to Px P bar, where P bar is a quaternion conjugate, is a linear map in X. Not only is it linear, it preserves the norm and also the orientation. And so its matrix, written with respect to the basis ijk, is going to be a matrix in SO3R. And what's more, this map is onto. And it's also a group homomorphism with kernel, which is plus or minus 1. And more importantly, given this X, you can easily find the P representing it. Please do remember that if P represents X, so does minus P, and you can work with either of them, okay? And finding this P is extremely simple. So if you give me the matrix, the 9 entries, the components of P are given by some quadratic equations. They can be solved simply by inspection. You don't have to, it's extremely simple, okay? So once you find this, finding the angle is also easy. So what you do is you find a vector perpendicular to P. It's very simple. Then take the cross product. I should have said, so once you find the P, the axis, this follows from elementary properties quaternions, is just the imaginary part of the P that you found. So this is easy to do this, and it's easy to find a basis for the orthogonal plane. And then you restrict your Px P bar to this orthogonal plane, and you will find the angle, okay? Point which is relevant to what I'll be discussing later is a different way of looking at this is you look at the Lie algebra of the unit quaternions. That turns out to be all the purely imaginary quaternions. You linearize this map, X goes to Px P bar. You'll get a map X goes to Qx minus Xq, where Q is in the Lie algebra. And your axis is simply all those X's which commute with Q, which is exactly essentially Q itself, okay? All those purely imaginary X's which commute with Q. So it's easy to do it this way as well. All right, what is the higher dimensional generalization? So I'm going to explain to you first how I would do this via finding eigenvalues, but that is now more complicated, but it can still be done. And then I'll explain to you how to do this via the generalization of quaternions, namely the spin groups. Or approach one, again, finding eigenvalues is actually straightforward. You'd think it's a quintic equation. It's not all that problematic, because once again, one is an eigenvalue. So you divide through, you're going to get a quartic equation. But this is not a generic quartic. It turns out to be what's called a palindromic polynomial. That is, its coefficients read the same backwards and forwards. And it's well known how to solve such PDEs. Essentially, in this particular, this sort of polynomial equations. And in this case, it'll turn out that it suffices to solve a quadratic equation. So you can find the eigenvalues. It's not a problem, the remaining eigenvalues. But of course, axis now is a little more complicated, because instead of finding just a square, you'll have to form this product, a square plus mu square identity, multiplied by a square plus mu square identity, whatever mu square are, those things can be found. And again, you will get a column, right? A non-zero column of this matrix is guaranteed to be an eigenvector. If the multiplicity is more than one, because this is a matrix in SO5, the algebraic multiplicity is the same as geometric multiplicity. So if the multiplicity can only be 3 if it is not 1, then there'll be 3 linearly independent columns. Okay, but that's a bit unsatisfactory, at least for me, because it just says do what you have to do, and that gives you the answer. But a little more insight is obtained by trying to mimic what the quaternion approach, and that goes through the notion of spin groups. I'm going to take a few minutes to explain to you in a pedestrian way what the spin groups are and how this is. So what is this? The unit quaternions are, of course, what's called big SU2. So that's a group of matrices. Likewise, a covering group of SO5 is SP4. This is the set of all 4x4 complex matrices, which are symplectic and unitary. For SO6, for instance, SU4, for SO7 is the so-called G2 and all that. So let me explain how this is briefly done. You begin with what's called Clifford 0n. So this is a real associative algebra spanned by some symbols, x1 to xn, together with the identity. And these xi's satisfy the following relations. Their squares are minus identity and the anti-commute. Xi xj is minus xj xi if I is not j. Now, and then what you do is just take all possible products. So one vectors will be spans of the xi's, zero vector will be just something proportional to identity. Two bivectors will be spans of x, linear combination of xi, xj, trivectors, four vectors, etc., till you get to five vectors, which are just x1, x1 all the way up to x5, for instance, in the SO5 case. All right, now on any Clifford algebra, by the way, I've restricted myself to Clifford 0n. As you can imagine, there's Clifford PQ, where P plus Q is n. I'm not going to go into that for this talk. But all these things that I've written here carry through for that case as well. If you don't mind, I'm going to get a little bit of coffee. So there are three important linear maps, rather algebra maps on Clifford algebras, which are of importance. The first is called reversion. So reversion is first a linear map. It is required to satisfy this homomorphism property, anti-homomorphism property, sorry. Phi rev AB is phi rev B multiplied by phi rev A. It acts as the identity on all one vectors, and of course, phi rev 1 is 1. The other famous operation is called Clifford conjugation. That too is an anti-homomorphism, but now it's required to act as minus the identity for all one vectors. And the grade isomorphism is just the composition of these two. It doesn't matter which order you do them. In other words, phi rev commutes with phi cc. And so these are the three important involutions. They're involutions because if you do them twice, you will indeed get back the original thing. Okay, so now in the Clifford algebra, there is a subalgebra called the even subalgebra. It is just zero vectors, two vectors, four vectors, etc., etc. But it's also the same thing as the fixed point set of the grade isomorphism. And it's known that this too is a Clifford algebra itself, okay? So for instance, the even subalgebra of Clifford 05 is Clifford 04. Okay, so now there is a subgroup sitting inside the even subalgebra, which is what is of relevance to us. It's defined by three conditions. So the first just says that it's sitting inside the even subalgebra. The second says that X Clifford conjugation is the inverse of X. And the third condition is a bit technical. It says, look at all those X's which satisfy the first two conditions, but throw out those which don't satisfy this. That is, you hit every V with X Clifford conjugate, what you should get should still be a one vector, okay? And it's known that this last condition is redundant or it's not needed if n is less than or equal to 5. So only when n is bigger than or equal to 6 do you have to really sit and work on this condition. The second important thing about Clifford algebras is they can all be realized as matrix algebra, subalgebras of matrices with entries either in the real numbers, complex numbers, or the quaternions themselves, okay? So that's what we'll do. So now I'm going to tell you what this generalizes to for SO5. So here's my basis of one vectors for the Clifford algebra 05. And these are all matrices. So these are the poly matrices, sigma x, sigma y, and there's a sigma z here. And this is just a Kronecker product, okay? So A Kronecker B is the matrix obtained by doing A11B, A12B as blocks. And if you do some calculation, I've not told you what the main, the reversion. So reversion, Clifford conjugation can all be realized as some matrix operation. So in this case, Clifford conjugation just turns out to be Hermitian conjugation. And reversion turns out to be X goes to this matrix inverse X transpose this matrix. So this matrix J2 direct sum minus J2, that is it's a block diagonal matrix. First block is J2, this is minus J2. J2 is exactly I sigma Y, okay? So 0, 1, minus 1. So if you do the calculations on the previous page, it turns out that spin 5 is exactly those matrices which are symplectic with respect to this signature matrix. That is, these are matrices so that X transpose J2 direct sum minus J2X equals J2 direct sum minus J2. This is not the standard realization of the symplectic form, and finding this signature matrix took us some work. It was not obvious, and we had to be sort of think on our feet to do it. Okay, so be that as it may, so this is this is essentially SP4, so it's not the standard version of SP4. If you want it to be the standard version, we have to change the basis vectors. That can be done, but I don't see any genuine reason to do so. Okay, we decided to call this Lie group, even though it is really isomorphic to SP4, as SP hat 4, capital SP hat 4. Accordingly, the Lie algebra is small SP hat 4. This is a 10-dimensional Lie algebra with a certain basis which can be explicitly written out, but I don't have space in the talk to tell you what this is. So it's some very explicit collection of matrices. Okay, so now to mimic that X goes to QX minus XQ, so X, the axis is those things which commute with Q. The analog would be, I'll fix an element in the Lie algebra. This is my analog of the Q. And I take a one vector. This is a combination of alpha Fi. And I seek those alpha I such that they will commute with this. So in other words, we think of the beta J as given. And I'm trying to find the alpha I so that AX is XA. And Emily wrote out these conditions. The equations characterizing this are this set of equations. So remember, in this, the beta i's are known. We're solving for the 5 alpha i's. And then we define these 5 quantities, which are concocted out of this beta j. Good. And then here's the first result. If all the beta j is 0, in other words, A is 0, then of course the fixed space is all possible alpha I, so that's R5. So this would correspond really to the rotation becoming the identity matrix, okay? If beta j is not 0 for at least one value of j, but big BK is a 0, and we can easily check this, then what you get is a 3-dimensional set of solutions, and you can find them explicitly. If you fix one particular beta j, which is non-zero, an explicit description can be found. I don't have space to write it, but this is fully doable. And if bk is not 0 for at least one value of k, so we are assuming beta j is not 0, and also at least one bk is not 0, then in fact the solution is a 1-dimensional space, which is given by a linear span of b1 to b5, okay? So in this case, we genuinely have a 1-dimensional axis, okay? So we can find the axis rather easily. And what we do now is also, I hope I have it here. Here it is. We have, so we also need to find this, the plane or higher dimensional space perpendicular to this axis. And we can do this also explicitly, okay? So this is, here's the theorem, which seeps into 2 or 3 pages. So here is the condition. In the first case, it's easy. There is no room, right? The axis was all of R5, so there's nothing. In this case, you can find, in the second case, you can find this by solving the system of equation. Again, you can do it explicitly. So this, even though it's linear, but we can write out the solution. And the last case, what we have is that the perpendicular plane, which will be 4-dimensional, will be the set of solutions to this. Okay, so this was at the level of SP, the Lie algebra SP4. So you may ask, how do you do? So you start with a given matrix in SO5, what should you do, right? The first thing, of course, is you should find the matrix in big SP4 which projects to it. And this may look formidable, but it is not at all hard to do. So in a recent paper of ours, we have shown how to do this in an explicit form. What we do is to decompose the original matrix in big SO5 into certain special matrices called Givens rotations. There's an explicit way to do it. You need at most 10 Givens rotations, but half the time you don't need it. It's much lower. And each of these Givens rotations can be easily inverted, okay? There's a bunch of quadratic equations that you have to solve, blah, blah, blah. It's easy to do. So I can easily find this y, okay? Then so one thing I could do is directly work with this y and try to find something which commutes with the y. The only problem with that is describing the solution will be far more complicated. It won't be as elegant as this. The main difference being the equations here are linear in the betas, right? So we don't have, what will happen if I do it directly at the level of y will be, I'll be getting quadratic equations. You can do it, solve that via Grosvenor basis, etc. But you, at each stage, you lose a certain degree of explicitness if you do that. So the other alternative is to find the logarithm within SP hat, logarithms are not unique in general, of y. And the remarkable thing is that in all but the generic case, I can find this x very easily. So let me tell you two situations. So first thing you do is check if so take your y and you split the y into its Hermitian part and its anti-Hermitian part. This is simple. The Hermitian part is y plus y star by 2. You check if this matrix is scalar, that is it proportional to the identity? If it is, you compute 1/4 its trace. So this is guaranteed to be of the form cos C, and any choice of C can be used, okay? And then this x can be recovered as C divided by sine C times A, where A is now the anti-Hermitian part of y, that is y minus y star by 2, okay? So if you add a different choice, C by sine C times A will be different from this x, but both of them will exponentiate to the same y. All right, supposing the Hermitian part is not scalar, then the next thing to do is check if the anti-Hermitian part is singular, all right, if it's got 0 determinant. If that is the case, I compute the C so that cos C is half of trace H minus identity plus 1. Any C again will do, and I can recover the X this way. Of course, the general case, if these two things don't work, of course, you have to diagonalize. So that is the only sort of fly in the ointment, if you wish. But this entire thing can be done at each stage. Everything can be written out in explicit form. And there's more so some of these things were done in Emily's thesis already. So let me also show you maybe here, right? So we go to this. So in this case, in the orthogonal plane, which will be 2-dimensional, the rotation will be doing a regular 2-dimensional rotation. It's easy to find representation for that 2-dimensional rotation. That is, the theta can be found. Here, the orthogonal plane is 4-dimensional. And instead of diagonalizing, what we can do is to represent the rotation restricted to this 4-dimensional plane as a 4-dimensional rotation. And 4-dimensional rotations can be represented by 2 unit quaternions. And we can write explicit formulae for these unit quaternions. So this is a complete description. And of course, there is a point beyond which, when you go to higher dimensions, SO7, etc., this is going to get progressively more complicated, right? So this portion, for instance, inverting the covering map is very easy to do. Finding these logarithms, etc., will therefore not be anymore that explicit. At least I don't expect it will be that explicit anymore, okay? But you could find the axis by working directly with this inversion, this y. It'll be a bunch of quadratic equations, and perhaps Grosvenor-Basis methods will give you that solution. The main point behind this is to say that for rotations, there are many representations available. Each of them provide different information. They all provide parameterizations of the orthogonal group. Which one is useful depends very much on the application. But what I hope to convey is these are not just generic matrices. They have a lot of structure. And if you use the structure, you can get some fairly explicit descriptions. And that's all I have. I would like to thank the organizers for inviting me. It's a big, big privilege. And I'm ready for any questions that you may have.
Participants, if you have any questions.
Instead of question, let me introduce myself, Professor Ramakrishna. This is Bhudal
Yes,
Sharma.
Dr. Sharma.
We have been corresponding and have been in touch. I'm so happy that you are able to make it and will be entering more, directly in some of the ways of FIM and all that. Welcome.
Thank you so much, Dr. Sharma. And once again, Dr. Sharma, Dr. PVS were all the people who introduced me to the world of FIM. I'm so grateful.
I'm a part of it now.
Thank you. All right. Anything else?
Is anybody wanting to say any comments or any questions? He gave such an elaborate speech on the rotation group, and he took it to the higher dimension and generalizations, and helped us find explicit formulae. Thank you, Professor.
Thanks to Emily.
Thanks, Professor, for such a lucid presentation.
Thank you.
No, the very difficult concept you put it to us, like it's so easy. It's not that easy.
Thank
So
you.
that comes only from experts' mouth. So hearing such expert like you, for the young research scholars and young staff members who are part of this session, they must be looking at you with an awe. Thank you very much for sharing your knowledge with us.
You can tell students of Stella Maris that they are themselves great individuals, and they also produce great individuals. Okay.
Yeah, thank you very much, Professor.
Thank you. All right, I'll stop sharing if you don't mind.
Yes, sir. Okay. Yes, sir, please.
Thank you. All right. I'm going to turn off the video. Okay.
You can turn off your mic as well.
Ma'am, shall I begin with the symposium now?
Yeah. Dana, before you begin the symposium, will you announce the other symposia that's going to happen, and then?
Yes, ma'am.
So I sign off. Thank you very much for the patient hearing.
Okay. So now in the same link, we will be continuing with the Symposium of Fuzzy Set Theory and Applications. Simultaneously, we are having 3 other sessions happening, starting at 6:30. We'll have paper presentations from statistics. Then in another link, there'll be classical analysis. And at 7, theoretical and computational nonlinear dynamics of condensed matter and their applications. So we will begin with the fuzzy set theory and applications symposium. So in this session, we are having 6 invited talk, followed by 6 paper presentations. Each invited talk will be for a maximum of 20 minutes, followed by some questions. So let us begin the symposium. The first speaker for the symposium is Dr. K. Ganesan, Department of Mathematics, SRM Institute of Science, and Technology, Katangulathar Campus, Chennai. His areas of interest are fuzzy optimization, operations research, interval analysis, ordinary and partial differential equations. Dr. Ganesan has 190 research paper publications in indexed international journals. He has co-authored 16 books in mathematics, which are used as textbooks in various programs. Dr. Ganesan has completed 2 research projects. 16 students have completed their doctoral degree under his guidance, and 3 are currently pursuing their research. Dr. Ganesan is a life member of the Indian Science Congress Association, Indian Society of Technical Education, Kerala Mathematical Association, International Association of Engineers, and Indian Mathematical Society. With this brief note, now I would like to invite Dr. K. Ganesan to deliver his talk on solving multi-objective, fully fuzzy, linear fractional programming problems. Over to you, sir.
Thank you very much, Dr. Dhanalakshmi, for your nice words.
Thank you, sir.
Dear friends, uh, I really very much thankful to the organizers, starting from Professor Felbin and her colleagues, for giving me this opportunity to interact with you this nice evening time. Uh, Today, I would like to share my ideas regarding the solution of multi-objective, fully fuzzy linear programming problems. Now, I would like to share the okay. Okay, dear friends, am I audible and is the slides are visible?
So your audio is clear, sir, but we could not see your slides.
Oh,
There is an option of share screen, sir.
yes. Come on.
Sir, is there any problem in sharing the screen, sir?
Share as options it comes,
Yes, sir. In that you
share.
can choose the window. You have to keep your file open, sir. It
Okay,
should not be minimized.
okay.
So when you click on the share screen, it will show you various options, whether entire screen or that particular file.
For that, I have to go to that.
Your presentation, yeah.
See the. Uh,
If your file is minimized, it may not show in that option, sir.
oh. Share 33 slides of that.
No. When you give share
Coming.
screen, it is. Have you selected the share screen, sir?
Uh, okay, there. Zoom. Actually, the problem is with my laptop. I am unable to open the laptop, but when I am using that mobile,
Okay.
it doesn't come. I don't know why it is. Just a minute. I'll
Yes, sir. Yes. Sir, or else can you mail me? I will share. I'll present from here.
Okay. Oh, I'll mail it immediately.
Yes, sir. Thank you.
Ma'am, have you received it?
Not yet, sir.
Oh, just a minute. I have sent it to Felby, ma'am. Oh,
Okay.
I,
Actually, I have sent you one mail now, so you can actually give it as a reply to that
yes,
now, sir.
ma'am, have you received it?
Sir, not yet, sir. I'll check. Yes, sir. Yes, sir. I have received. I'll download and I'll play that. share that, sir.
Okay.
Sir, I have presented the screen, sir.
Yeah, yes, ma'am.
Yeah.
Yes, ma'am. Yes, ma'am. Yes, ma'am. Okay, shall I continue?
Yes, sir.
Okay, okay. Dear friends, today let us discuss the solution procedure for multi-objective fully fuzzy linear fractional programming problems. Next slide, ma. Okay. Linear fractional programming is a generalization of the linear programming problem. We know that the objective of a linear programming will be a linear function, whereas the objective function of a linear fractional programming problem will be a ratio of two linear functions. A linear program can be regarded as a special case of linear fractional programming in which the denominator is the constant function, maybe 1. Next. Both the linear programming and the linear fractional programming represent optimization problems using linear equations and or linear inequalities, which for each problem instant define a feasible set. Fractional linear programs are a richer set of objective functions. Informally, linear programming computes a policy delivering the best outcome, such as maximizing the profit or minimizing the cost. Whereas a linear fractional programming is used to achieve the highest ratio of outcome to cost, the ratio representing the highest efficiency. Next. The linear fractional programming problem, which has been used as an important planning tool in recent years, is applied to different disciplines such as engineering, business, finance, economics, and so on. Linear fractional programming problem is generally used for modeling real-world problems with one or more objectives, such as profit upon cost, inventory upon sales, output upon employee, and so on. Generally, when trying to solve any physical problem which may be modeled as a linear programming problem or as a linear fractional programming problem or any mathematical programming such as quadratic, convex, whatever it may be. The decision parameters of the model should be known precisely. But in real world situations, it is very difficult problem or
some of the parameters representing the data for the problem may not be known precisely. In such cases, the unknown parameters or the vague parameters can be modeled as fuzzy numbers, and the corresponding problem, even if it is a linear programming problem, we may call it as a linear fractional programming, fuzzy linear programming problem. If it is a linear fractional programming problem, we call it as a fuzzy linear fractional programming problem. Many others have discussed about the solution concept for fractional linear programming problems under the precise environment as well as under fuzzy environment. There are certain others who have discussed the fuzzy fractional linear programming problem with a single and multi objectives in the recent years. These papers are taken or published during the year 2019. Most of the others, while dealing with the fuzzy fractional linear programming problem, they try to defuzzify the fuzzy linear fractional programming problem to equivalent Cripps linear fractional programming problem by applying the known ranking techniques. But we try to solve the fuzzy linear fractional programming problems without affecting the fuzzy nature of the problem. In this talk, let us discuss the solution of a multi-objective, fully fuzzy linear fractional programming problem without affecting its fuzzy nature. That means without converting to an equivalent Cripps problems. For that purpose, we need some basic concepts regarding the fuzzy numbers, and then the fuzzy arithmetic, then the concept of ranking of fuzzy numbers. As we are well known to the concept of fuzzy set theory, a fuzzy number will be a fuzzy set defined on the set of real numbers whose membership function is piecewise continuous, normal, and convex. Simply, a fuzzy number defined on the set of real number R is a convex and normalized fuzzy set whose membership function is piecewise continuous. Simply, you can say. And there are different types of fuzzy numbers. We restrict ourselves to this talk to the type of triangular fuzzy numbers. A triangular fuzzy number defined on the set of real number R will have this membership function whose diagrammatic representation will be a triangle, and we denote this triangular fuzzy number A tilde by a triplet A1, A2, A3, and we use f of r to denote the set of all triangular fuzzy numbers define the real numbers R. And for the computational purpose, the triangular fuzzy number can be represented in a convenient form, which we call it as a parametric form of the triangular fuzzy number. The triangular fuzzy number A tilde can also be represented as a pair A tilde, which is A lower bar, A upper bar of functions A lower bar of R and A upper bar of R, where R belongs to the closed interval 0, 1, which satisfies the following requirements. A lower bar R is a bounded monotonic increasing left continuous function, and A upper bar of R is a bounded monotonic decreasing left continuous function. And A lower bar of R is less than or equal to A upper bar of R. And here this A lower bar and A upper bar are the endpoints of the alpha cut. We know that alpha cut of any Gaussian number is an interval. The left limit of the interval is A lower bar and the right limit is A upper bar. So the triangular Gaussian number A tilde can also be represented as A tilde, which is A naught, A lower star, A upper star, where A naught is the location index of the fuzzy number A tilde, which is nothing but the one cut. A lower bar of 1 plus A upper bar of 1 divided by 2, which is A naught. And A lower star is given by A naught minus A lower bar, which is the left fuzziness index, and A upper star is given by A upper bar minus A naught, which is the right fuzziness index. Now, Mingmo et al. Have proposed a new fuzzy arithmetic based upon both the location and fuzziness index functions. The location index number is following the usual arithmetic, whereas the fuzziness index functions are considered to follow the lattice rule, which is the least upper bound and the greatest lower bound. And that is for any A tilde and B tilde belongs to the lattice L. We define A or B, which is the maximum of A tilde and B tilde, and A and B, the greatest lower bound, which is the minimum of A tilde and B tilde. So by using this, the arithmetic operations on any two fuzzy triangular fuzzy numbers A tilde and B tilde, which are represented in terms of their parametric form, are defined as I said, that the location index follow the usual classical arithmetic, and the left fuzziness index and right fuzziness index follows the lattice rule. That's why the sum of, the addition of two fuzzy numbers A tilde and B tilde is A naught plus B naught, comma, maximum of A star, comma, B star, comma, maximum of A star, comma, B star. Both of the, that means A lower star, B lower star for the right index, A upper star, B upper star. Similarly, for the other operations, subtraction, multiplication, division, while defining the division, one more the condition should be provided. The division is possible provided only when the denominator B naught should not B naught is not equal to 0. See here, the very important thing here is the general, the classical or the usual fuzzy arithmetic, the traditional fuzzy arithmetic, while defining the division, the denominator fuzzy number should not contain 0. But here there is a relaxation in that condition, that it may contain 0. The denominator fuzzy number may contain 0, but its core or its location index should not be 0. there is a relaxation in that condition while using this fuzzy arithmetic operations. And other thing, and we will seeing in the example, while applying the traditional fuzzy arithmetic operations, while manipulating the fuzzy numbers with that traditional fuzzy arithmetic operations, the vagueness of the resultant fuzzy number will be more and more. Whereas while applying this Mingmo et al.'s fuzzy arithmetic, the vagueness is somehow controlled to a tolerable limit. Now, the next thing, we know that while we dealing with the optimization problems, we should be able to identify the maximum or minimum. Wherever we are considering the profit, we should be able to identify the maximum. And wherever we are discussing about the cost, we should be able to identify the minimum. So such cases, we should be able to compare the cost as well as the profits. But here, it is very difficult to compare the fuzzy numbers directly. So we are having the function which is called as the ranking function, which is defined from the set of fuzzy numbers to the set of real numbers, defined by many ways. There are a lot of ranking functions are available. We are considering only this ranking function for any triangular fuzzy number a tilde. Its ranking is defined by a upper star plus 4a naught minus a lower star divided by 4 while applying the parametric form, and which is similar to a lower bar plus a upper bar plus a naught divided by 4 while having that alpha ket of that triangle fuzzy number. By using this ranking function, we can compare any two triangular fuzzy numbers a tilde and b tilde by this rule. A tilde is greater than or equal to b tilde if and only if rank of a tilde is greater than or equal to rank of b tilde, and a tilde is less than or equal to b tilde if and only if rank of a tilde is less than or equal to rank of b tilde. A tilde is equivalent to b tilde if and only if rank of a tilde is equal to rank of b tilde. And moreover, when rank of any triangular fuzzy number, it may be a tilde, when rank of a tilde is equal to 0, we say that the triangular fuzzy number a tilde is a 0 fuzzy number. When rank of a tilde is greater than or equal to 0, then we say that the triangular fuzzy number a tilde is a non-negative triangular fuzzy number. When rank of a tilde is strictly greater than 0, then a tilde is said to be a positive triangular fuzzy number. Okay, using this basic concepts, let us go for the fully fuzzy linear fractional programming problems. A general form of the fully fuzzy linear fractional programming problem is given by this equation. Here the objective function having the fraction, numerator is a linear function, denominator is also a linear function subject to the set of constraints and the non-negative restrictions. Here our in this problem we consider all the parameters such as aij tilde, bi tilde, cj tilde, xj tilde, everything as triangular fuzzy numbers. Similarly, the general form of multi-objective fully fuzzy linear fractional programming problem is given by this equations. So there are k objectives subject to the same set of constraints, where each objective is of the form is that I of x tilde is ci tilde x tilde plus alpha I tilde divided by di tilde x tilde plus di tilde. Here are the vectors, that like c1 x1 plus c2 x2, likewise it will go. And the constants alpha I tilde, beta I tilde are scalars. They are fuzzy numbers. Now, we call that multi-objective, fully fuzzy, linear fractional programming problem as problem number 1, and we can define an equivalent problem which is a fully fuzzy linear programming problem. That means it is a non-fractional, the non-fractional problem corresponding to the previous fractional problem. Here this I tilde star will be the optimal value of each objective function in the given multi-objective fractional programming problem, where xi star is the optimal solution corresponding to the ith objective function. So if there are k objective functions, there will be k objectives of k optimal x tilde, and the corresponding z tilde will be there. And there is a theorem, an important theorem, which gives the solution. That means, the relation between the fractional and the non-fractional linear programming problems, or the relation between the problems 1 and 2. If x star is a Pareto optimal solution of the problem 1, the problem 1 is nothing but the multi-objective, fully fuzzy linear fractional programming problem. And problem 2 is the not multi-object, it is single objective. It is a single objective, fully fuzzy, non-fractional. That means linear programming problem. So for any linear programming problem, we may able to get an optimal solution. Whereas when we consider the multi-objective problems, it is not possible to get the optimal solution because there will be conflicting solutions. Unless you increase or decrease the one solution, you will not get you will not maximize or minimize the other one. So there will be only the compromise solutions instead of optimal solutions. We call that compromise solution as a Pareto optimal solution. So when x star is a Pareto optimal solution of the multi-objective, fully fuzzy linear fractional programming problem, if x star is an optimal solution of the single objective, fully fuzzy linear programming problem. Using the theorem only, we will find a Pareto optimal solution of the multi-objective, fully fuzzy fractional linear programming problem. Now there is an example. We are having an example with the 2 objective functions and 2 constraints, and we consider all the parameters as fuzzy numbers, and we assume that all the fuzzy numbers are triangular fuzzy numbers type, and we define the fuzzy numbers 6 tilde, 5 tilde, and other 2 tilde, 7 tilde, all these things in such a way in the triangular form which will be represented here. So that means the fuzzy number 6 tilde is represented as 468, and the other fuzzy number 5 is represented as 456. Likewise, all these things. Now, this is our multi-objective, fully fuzzy linear fractional programming problem involving triangular fuzzy numbers. Now, we are going to solve the problem by taking one objective function at a time. That means we are going to have this problem as two single objective fractional linear programming problems. So first objective along with the constraints, one problem, and then the second objective along with the constraints as a second problem. Now, the problem one, we consider the first objective function with the available set of constraints. Now, by assuming properly, first we are going to convert the fractional programming problem into a non-fractional programming problem. So this is our assumption. By assuming the denominator as t tilde, the problem becomes of this kind. So here the fractional programming becoming a fuzzy linear programming problem involving three variables. That means the fully fuzzy fractional linear programming problem with the two variables becoming a fully fuzzy linear programming problem involving three variables with the three constraints. Now, once we reduce the fractional programming into non-fractional programming problem, we can apply any type of the available method to find this transformed, the reduced problem. And this time, let us try to apply the concept of solution of system of equations to solve this linear programming problem. We are going to apply the Gauss elimination method to solve this linear programming problem involving three variables. Now, by assuming this, so because again this becoming non-linear, actually we are converting this again to linear, this form, by assuming x1 tilde t tilde as y1 tilde and x2 tilde t tilde as y2 tilde, the problem becomes a linear programming problem, a fuzzy linear programming problem, single objective fuzzy linear programming problem involving three variables, t tilde, y1 tilde, y2 tilde. And now this LPP can be reduced to a system of linear equations. They are okay. Now we are representing.
So we have an.
It is very easy to manipulate with the parametric form. So
we have another 5 minutes to.
In terms of their parametric form, that means in terms of the location index and fuzziness index, we are getting this fuzzy linear programming problem, and it is reduced to system of inequalities, the linear system. And now, by applying the Gauss elimination method using the proposed arithmetic operations, we are able to get the values of z1 tilde, y1 tilde, y2 tilde, and t tilde. After getting these values, actually we have assumed that x1 tilde is nothing but y1 tilde by t, x2 tilde is nothing but y2 tilde by t. So from these things, it is we are able to find the values of x1 tilde and x2 tilde. So after getting these values of x1 tilde and x2 tilde, we should represent the original problem 1, the solution for the original problem 1. Now we are getting the optimal solution of the single objective fuzzy fractional linear programming problem. The problem 1 has a maximum of z1 tilde is 1.275, 2 minus 2r, 2 minus 2r with the values of x1 tilde and x2 tilde. In the similar way, we can have the second problem also. That means the second objective along with the given constraints, it can also be represented as the second problem can also be solved as we have done in the case of the first problem. Again, by using that Gauss elimination method, we have obtained the optimal solution for the second problem as Z2 tilde, which is 0.5675, 2 minus 2r, 2 minus 2r with the values of x1 tilde and x2 tilde. And you will see that the values of x1, x2 for the problem 2 will not be same as the values of x1, x2 for the problem 1. So now we are going to, after solving the individual objectives, as we are having two objective functions in the given problem, we have solved two separate problems as problem 1 and 2. We obtained the optimal solution of both the problems. And now we are going to combine, or we are going to transform the multi-objective fractional linear programming problem to a single objective linear programming problem. So we are going to convert. This is the rule for it. Now that we are having already conversion of the multi-objective linear fractional programming problem to a single objective linear programming problem. So by using the two objectives and by using that optimal solutions of both problems, above two problems, we modify this the multi-objective to a multi-objective fractional to a single objective non-fractional at this kind, subject to the same set of constraints. Now, the given bi-objective or multi-objective linear fractional programming problem becoming this fully fuzzy linear programming problem. Again, we are going to solve this by applying the Gauss elimination method. Become the system of linear inequalities, and by solving this, we will get the Pareto optimal solution or the compromise solution for the given multi-objective fully fuzzy linear fractional programming problem is given by the objective value of the first objective Z1 and the second with the values of x1 tilde and x2 tilde. Now, the solution obtained is in terms of the parametric form. It is in terms of R. And we know that our R belongs to the closed interval 0, 1. By giving different values for R, we will get different solutions. That means different solutions with the different vagueness. When R is equal to 1, the problem becomes a Cripps linear, the Cripps problem. So you'll get all these, 1.5 comma 1. All these things becoming the same value, and you can give any value. You can give r is equal to 0, r is equal to 0.1, 0.2, 0.3, likewise. So by using this arithmetic operations and this parametric form, as well as without converting to the classical form, we are able to solve the problem without affecting its fuzzy nature. Also, we are able to get different solutions for different values of r. So the conclusion is, here we have proposed the method, that means the Gauss elimination method for the solution of fully fuzzy linear, multi-objective fully fuzzy linear fractional programming problem without converting to its equivalent Cripps form. From the table, it is evident that the proposed method gives flexibility to the decision makers to choose their preferred solution by selecting suitable R, whereas the other methods does not provide such facility to the decision makers. The main thing to this method of using this parametric form is to get the flexibility, to get more choices to the decision maker to choose their preferred solution by suitably selecting the R. And these are references, all of the recent papers. Okay. Thank you. That if you have any queries, please let me know.
Thank you, sir. We can have one or two questions now. I have unmuted, I have given the permission for Mr. Omdat Sharma. So if you have any
Hello?
queries, you can unmute and you can ask, sir.
Am I audible?
Yes, sir.
Hello?
Yes, sir. You're audible, sir. Sir, you're audible, sir.
Okay. If there is any query, please let me.
Yeah,
Yeah,
one of the participant has raised hand. Mr. Omdut Sharma, you can ask the question.
Any other questions from the participants?
You can put it in the chat.
Okay. Sir, I think we don't have any questions. So thank you, sir. Thank you for your insightful talk on linear fractional programming problems in the fuzzy environment. Thank you, sir.
Thank you. Thanks for the organizers for giving me this opportunity. Thank you.
The second speaker for the symposium is
Shall I
Dr.
leave the meeting?
Yes, sir. Yes, sir. Thank you for joining, sir.
Okay.
Dr. B. Prabha is a professor of the Department of Mathematics, SSN College of Engineering, and has 32 years of teaching and research experience. Her areas of research interest includes rough set theory, soft set theory, algebraic graph theory, and their applications. Dr. B. Prabha is the recognized supervisor of Anna University, Chennai, VIT University, Vellore, and Sri Shekrendra Saraswati Vishwa Mahavidyalaya University, Kanchipuram. Under her guidance, 4 students have been awarded their PhD degree from Anna University, Chennai, 2 students from VIT University, Vellore. Currently, 4 students are pursuing their PhD under Anna University, Chennai. Dr. Prabha has received Outstanding Educator and Scholar Award in the 8th Teachers' Day Awards 2017, powered by NFED, and Best Researcher Award for the year 2009 by SSN College of Engineering. She has published 2 research chapters in Trends in Mathematics Springer Book Series 2018 and published 110 research papers in indexed international journals and conference proceedings. She has co-authored 6 books. Dr. Prabha has served as a reviewer for Journal of Intelligent and Fuzzy Systems, International Journal of Fuzzy Systems, Fuzzy Sets and Systems, Discrete Mathematics, Algorithms and Applications. Now I invite Dr. B. Prabha to deliver her talk on lattice structure on fuzzy beta and neighborhood based soft rough sets. Over to you, ma'am.
Good evening to all of you. Am I audible?
Yes, ma'am. Yes, ma'am. You're audible.
Yeah. Just I'll put my video off. See, actually, my topic is fuzzy beta neighborhood based soft rough sets. Basically, I start with rough set. Just a minute now. One not So before I start showing the PPT, I would like to say a few words about rough set theory. PPT. PPT. Okay. See, rough set theory was introduced by Z. Pollock in the year 1965. Since then, it has been widely used in various applications of data analytics, neural networks, artificial intelligence. To this rough set theory is used to deal with uncertain and incomplete information in an information system. Normally, many are see there are 2 ways um, of the researchers deal with the concept of rough set theory. One is on the application side in applying it in neural networks and artificial intelligence and data analytics. And the other method is the algebraic study of rough set theory. To introduce the rough set theory, we consider a non-empty finite set of objects U and an equivalence relation R defined on U. See, the concept of rough set theory started like this, with a non-empty finite set of objects U and an equivalence relation R defined on U, and this is called as an approximation space. For every subset X of U, we define a pair of sets called as a lower approximation space and an upper approximation space. The lower approximation space will consist of the set of all equivalence classes which are completely contained in X, and the upper approximation space consists of those equivalence classes that has a non-empty intersection with X. So the ordered pair of lower and upper approximation is called as a rough set. And in this work, see, this concept was extended by taking more than one equivalence relation on U. Suppose if U is a non-empty finite set of objects with two equivalence relations R1 and R2, then for corresponding with for any subset X of U, with respect to the equivalence relation R1, we will have a rough set, and with respect to the equivalence relation R2, we will have a rough set. And this way of twin rough sets will help us in comparing the attributes of the objects in the universal set. And again, this can be extended in introducing more than two equivalence relation on U. Suppose if I have k equivalence relations on the universal set U, called as the set of objects which is non-empty and finite, then with respect to, for any subset X of U, with respect to each of these equivalence relations, I will get a rough set. And this way of writing a K rough set is widely used in many real-time applications. Then comes to the concept of soft sets. Soft set is again defined on a non-empty finite set of objects U and a function. Soft set is a function capital F, which is a function from A to power set of U, where A is the set of attributes that the objects will possess. And many authors clubbed the concept of rough set theory and soft set theory, and many algebraic study as well as on the application side, several work has been done in this direction. Now, in my today's talk, I am going to club or introduce a fuzzy set on the objects, and then define a rough set called as fuzzy beta neighborhood based soft rough set. For that, I consider an approximation space I is equal to U F A. This is called as a covering based fuzzy approximation space, where U is a non-empty finite set of objects and A is a non-empty finite set of attributes or those possessed by the elements of U, and here I am assuming A is also finite. And For each A belong to A, mu A is a fuzzy set and mu A is a function from u to 0, 1, where mu A of x is the degree of membership of the attribute A that the object X possesses. Mu A of X belong to the closed interval 0, 1, which shows the degree of membership of the object of the attribute A that the object X possesses. Okay. And what about capital F? It is a subset, that is, F is a function from A to power set of U such that union A belongs to A, F of A is U. If the function F satisfies this condition, union A belong to A, F of A equal to U, it is called as a covering based subset. Okay, so we consider an information system I is equal to U, F, A. U is a non-empty finite set of objects and A is a set of attributes that the object possesses, and the degree of membership of the attributes that each object will possess is given by the membership function mu A for each A, and F is a subset, covering based subset. Okay, with this, the objective is for each element beta in the closed interval 0, 1, and for each object X belong to U, I want to find those attributes which are greater than or equal to beta. The degree of those attributes should be greater than or equal to beta. And hence, I go for defining a set n beta of x equal to the set of all A belongs to A such that mu A of x is greater than or equal to beta. So what is the meaning of this? This set is basically a subset of the set of attributes. Here, I am choosing an element x belong to U and beta belong to the closed interval 0, 1. And this set will collect those attributes whose membership value is greater than or equal to beta, the chosen beta. And hence it is a subset of the set of attributes. Now, with this subset, I am going to define another set n beta tilde of x, n beta tilde of x. This set consists of the set of all y belong to U such that mu A of y is greater than or equal to beta, mu A of y is greater than or equal to beta, but where this A is chosen, A belong to n beta of x. So I want to actually find a neighborhood of the chosen object x. Please remember that rough set can be defined, for every subset of U. For every subset of U. So that is a general way of defining a rough set. Now, I am using this degree of the attributes that each of the objects in U possesses. I am using that concept to define a subset corresponding to each of the objects in U. So, I have chosen an object x belongs to U and the neighborhood of x is denoted by n beta tilde of x consists of the set of all y belongs to U such that mu A of y greater than or equal to beta. So, suppose if I choose my beta as 0.7, first in the n beta n 0.7 of x, will take those attributes whose membership value is greater than or equal to 0.7. So this is a sort of reduction on the set of attributes, and on reducing or on minimizing the attributes subject to the degree 0.7, I am choosing the neighborhood of X that also has the membership value greater than or equal to 0.7. And I call this set n beta tilde of X as the fuzzy beta neighborhood of the object X in U. Okay. So for each object X belong to U, I am able to find this n beta tilde of X is a subset of U, whereas n beta of X is a subset of the set of attributes, and n beta tilde of X is a subset of U. So for every object X belong to U, I am able to generate a beta neighborhood in U. This beta neighborhood can be used to define a rough set. But we have a soft set capital F defined on U, which acts as a covering. That is union A belong to A, F of A is U. Now take any X belong to U, and the beta neighborhood based soft rough set of X is defined by beta RS of X is equal to n beta lower of X, comma n beta upper of X. This lower and this simply a notation for the ordered pair of lower and upper approximation of the rough set defined for this beta neighborhood. This is simply a notation n beta lower of X and n beta upper of X. What actually this n beta lower of X is? It is a set consisting of all f of A. Remember that capital F is a function from A to power set of U. So this n beta lower of X equal to union of f of A, such that f of A is completely contained in n beta tilde of X. N beta tilde of X is a subset of U. I am taking those f of A which is completely contained in this neighborhood of X. In fact, I am taking those elements of U in f of A which is completely contained in the neighborhood of X, and n beta upper of X consists of union f of A such that f of A intersection n beta tilde of X is not equal to empty, and therefore this set n beta upper of X consists of all those elements in f of U such that its corresponding f of A has a non-empty intersection with at least some of the members of f of A will be in the neighborhood of X. So this lower approximation gives the definite members of the neighborhood, and the upper approximation gives the possible members of the neighborhood of X. And hence this is a lower approximation space, n beta lower of X, and n beta upper of X is the upper approximation space, and this ordered pair is denoted by beta RS of X, and I call it as the beta neighborhood based soft rough set. So what is the use of this? Actually, as I told you already, dealing with the concept of rough set theory is in two ways. One is the algebraic study, and the other one is its applications. So if you want to have an algebraic study of this way of defining rough sets, you can go for the study of the partial ordering relation, lattices, and so on and so forth. And if you want to study the application part of this can be used. For example, if you take the universal set as the set of employees in an organization, the attributes can be taken as their experience, age, qualification, other skills, hardworking, and so many things can be taken as the set of attributes. And whatever the degree of membership that you want to have for each of the employees, you can fix that. And then for each of the employee, you can take their neighbors and then find their asset and then have a clear and clear comparative analysis of the employee value proposition or employee engagement, and those parameters can be completely studied using this way of defining the research. Now, um, now we have defined the beta RS of x, and for each x belong to U, I have a corresponding set beta RS of x. Select all such ordered pairs and put it in a set, and that set I am calling it as T beta. T beta is set of all beta RS of x such that x belongs to U. And now uh, that, this is an algebraic perception of this definition. So I can define a relation R beta on T beta. We know that a relation on a set is a subset of the Cartesian product. So I want to define a relation R beta on T beta. It consists of the ordered pair beta RS of x comma beta RS of y, because I am fixing beta now. T beta or beta. Okay, I am fixing beta, and on T beta I am defining a relation. I denote it by or beta consists of beta RS of x comma beta RS of y, such that beta RS of x is a subset of beta RS of y. So this is a usual inclusion relation, is it not? So elements are ordered pairs, um, and inclusion relation is a partial ordering relation. Partial ordering relation means it will be reflexive, anti-symmetric, and transitive. Okay, and I hope we all are. This is a very basic concept. So this R beta is a partial ordering relation on T beta, and hence any set equipped with a partial ordering relation is called as a poset. So I can call this T beta as a poset. Okay, so by fixing one beta in the closed interval 0, 1, I get a poset. Now, if I vary this beta, what will happen? You'll see. I define a function. Okay, this is another way of representing the same. F beta is a function from U to T beta defined by F beta of x is equal to beta RS of x. Okay, on varying beta, I get a collection of sets. I denote that by f tilde equal to set of all f beta collection of functions. You can take like that, or this can be taken as collection of t beta, where beta belongs to closed interval 0, 1. Okay, so if I take this set of all t beta such that beta for easy understanding, I can take this f tilde as set of all t beta such that beta belongs to the closed interval 0, 1. Then it is a set of sets, collection of sets, is it not? Collection of sets. And these clusters, does it possess any property? Does it possess these clusters of cells, rough cells? Does it possess any property? Yeah, it has a property that for alpha beta belong to the closed interval 0, 1, with alpha greater than or equal to beta. If alpha greater than or equal to beta, for each alpha RS of x in T alpha, for each alpha RS of x, it is an ordered pair and it is an element of T alpha. For each alpha RS of x in T alpha, there exists a beta RS of y in T beta such that alpha RS of x is contained in or equal to beta RS of y. So it satisfies this property. And um, first, I will explain this with an example.
Ma'am, sorry to interrupt. You have another
Yeah,
3 minutes, ma'am.
yeah, I will do.
Thank you, ma'am.
Yeah. So consider just quickly, I'll go through this example. I equal to U, A, F. U is 4 elements x1, x2, x3, x4. A is A1, A2, A3. And I define the offset f of A1 equal to x1, x3 and f of A2 equal to x2, x4 and f of A3 is x3. And the function mu, the showing the degree of membership of the attributes on each of the objects is depicted in this table. And here, on the first row, point 2 represents the degree of membership of the attribute A1 that x1 possesses, like that. And this is an easy way of representing that fuzzy set. Um, Now, first I took beta is equal to zero point 0.1. So in this table, n beta of x, n beta tilde of x. I told you n beta of x is a subset of A and n beta tilde of x is a subset of U. As 0.1 is the least value in this table, the degree, least degree. Uh, uh, I have on finding n beta of x, on the first row I have to take those attributes corresponding to x1. If I want to calculate, I have to on the first row I have to take those attributes whose membership value is greater than or equal to zero point 0.1. As 0.1 is the least value, all the attributes A1, A2, A3 will come under this. That is why all the elements of the second column are A. And if I take all the objects and yeah, the neighborhood of x1 will be whole of u and x2 will be whole of u, and the corresponding rough set for u, the corresponding rough set will be u comma u. So this is a table correspond showing the uh, beta rough set corresponding to beta equal to 0.1. Now when I take beta equal to 0.2, come to this table. In the first row, I have to take those attributes whose membership value is greater than or equal to zero point 0.2. So it is A1 and A3. So for x1, A1 and A3. And now I have to restrict with these two attributes for x1 to find n beta tilde of x. So with A1 and A3, I have to take those objects of u whose value is greater than or equal to zero point 0.2. So x1, x2, x3, x4 will not come under this because corresponding to x4 the attribute degree of A3 is 0.1. So that is those neighborhoods are depicted in this third column. Now for each of the objects x1 I have a subset n beta tilde of x1. Like that I have created the neighborhood for each of the objects, and once the neighborhoods are created, corresponding rough sets or can be calculated using the soft set. Similarly for beta equal to 0.3, I have a cluster of rough sets, and when beta equal to 0.4, I have a cluster of rough sets. And here 0.4 is greater than or equal to zero point 0.3, and you can check that um, for each of the elements in the last table, I am able to find a corresponding element in the previous one, such that this is a subset of that, and that is the property that I have showed you. And each of the clusters will be a process, and the future work in this direction is to have a more detailed algebraic study on this clusters of rough sets and applying this in real-time problems. And I think I can stop with this, and I take this opportunity to thank Sister Rosie Professor Selvin and Professor Kennedy, Dr. Venugopal, Dr. Badmapriya, and all the organizers who have taken a lot of initiatives and gave me a wonderful opportunity to share some of my thoughts on Russet theory. Once again, I thank you all. If you have any queries, you can ask now.
Thank you, ma'am. We can have few questions. So,
I think my questions I will reserve for a later time to have a private discussion with Prabha.
Yeah, surely.
I think we don't have any questions, ma'am. Thank you, ma'am, for the informative session on the fuzzy beta neighborhood on rough sets. Thank you, ma'am. I now invite Professor D.S. Huda, Honorary Professor in Mathematics, GJ University of Science and Technology, Hisar, to chair the next session.
Professor Huda? Professor Huda?
Yes. Are you listening?
Yes, sir. We could hear you, sir.
Yes. Who is the next speaker? I am.
No, sir. You have to chair the next session, sir.
No. You see, continue, please. You see, it is very difficult for me because I am unable to. I don't know about that speaker. Who is speaker?
I had sent you the information, sir, already.
No.
Okay, it doesn't matter. It's okay, sir. It's okay.
Because I don't know have any information about the speaker and all this. Please continue. I will speak next lecture. I will deliver. Okay, my talk will be the next. Thank you, Pelvin, for you see.
It's okay, sir. It's okay. We understand.
Because it will not be possible for me.
It's okay, sir. It's okay. We'll take it.
Okay.
Then I just continue with Sudhakar.
Yes, ma'am. Our next speaker is Dr. Sudhakar Chandran, Department of Mathematics, Applied Sciences, Middle East College, Muscat, Sultanate of Oman. He has over 20 years of experience in teaching and research. He has published around 12 research papers in national and international journals. He is a reviewer of journals of IEEE, Elsevier, and Springer. His research areas are the fuzzy numbers, data science, technology in education, and child education. Professor has organized several conferences and has also completed 3 research projects funded by Indian and Oman research institutions. He has received several awards, to name a few: recipient of Best Teacher Award in 2000 by Hindustan University and Best Innovative Teaching Practices in 2012 by Middle East College. Thank you, Professor, for accepting our invitation and sharing your valuable time with us. Over to you, Dr. Sudhakar Chandran.
Thank you, Dr. Lakshmi. Thank you, Dr. Felben Kennedy, for giving me this chance. I think I'm audible, right?
Yes, sir, you're audible, sir.
Let me share my screen. full with audio. Version 2 version 2 sorry ma'am, just a few minutes.
Hello.
Yes, yes, sir, Professor Huda.
I can deliver. You can, you see, pass on to next time. Next speaker he can be. If there is difficulty, let me allow to present. Okay, and he can deliver after me. There
So
is
we'll
no harm.
check, so we'll let you.
He is facing some difficulty. Okay, because time is going on.
Felben, ma'am. Dr. Sudhakar, is it okay if Professor Huda does now? And you can do it next?
No issues. If he's ready, let him present, then I will continue next. No issues.
Okay, sir. Thank you so much, sir. Thank you. Professor Huda, I now invite Dr. Judani Cynthia to chair the session.
Good evening. It is my privilege to introduce the next resource person for the session, Professor D.S. Huda, Honorary Professor in Mathematics, GJ University of Science and Technology, Hisar, and Advisor to ABV Hindi University, Bhopal. Professor Huda has held several prestigious positions. To list a few, he was a principal of CRM Postgraduate College, Hisar, from 1985 to 87, Professor and Head, CCS, Haryana Agriculture University, ZA, from 1994 to 98. Pro Vice Chancellor of Kurukshetra University from 2002 to 2003. Professor and Head, JIET, Guna, from 2003 to 9. And Dean Research of JUET, Guna, from 2009 to 15. Professor has published around 108 research papers, 26 popular articles, and has presented research papers in more than 25 national and international conferences. He has also published 11 books. Professor has traveled across the globe to several reputed institutions as resource person. He is the recipient of 10 prestigious awards of both national and international forum. Sir, it's indeed a great honor for us to have you as a resource person. May I now invite you to present your talk on application of fuzzy soft and interval valued fuzzy soft matrices in dimension reduction and medical diagnosis. Over to you, sir.
Oh, please.
Sorry for the delay. There are some technical glitches from our side. Professor, we have shared the screen, your PPT. You can unmute and speak.
Yes, are you hearing?
Yes, Professor, very much.
Are you hearing?
Yes, Professor, we can hear you
Okay,
clearly.
okay, then I am thankful, Professor Felbin, giving this opportunity. I will be speaking on application of the fuzzy subset intervalued fuzzy soft matrices in dimension reduction and medical diagnosis. Next, next, yes, main points of the my talk is introduction, some basic concepts, fuzzy soft matrix with application data dimension, reduction, interval valued fuzzy soft matrix and its application in medical diagnosis, discussion and conclusion, then references. Next, fuzzy set was introduced by ZA and was extended to interval valued fuzzy set by Gortsvinin 6 and Tuxen to represent the degree of membership of an element by interval rather than exact membership value. Subset was insulated by Molesto to deal with the uncertainty due to vagueness. Later on, Maggi et al. Defined fuzzy subset as the hybridization of fuzzy set and subset. Young et al. Presented the concept of interval-valued fuzzy subset by combining intervalued fuzzy set and soft set. It is one of the important area for dealing with the uncertainty present in most of our real-life problems. Next. Fuzzy soft matrices are used in presenting fuzzy subset and intervalued fuzzy subset and representation of several advantages. So, and the concept of interval values for this subset matrices is the generalization of fuzzy matrices by extending the maximum in operation on fuzzy algebra. Also, the parameterization tool of interval valued of fuzzy matrix enhances the flexibility of the application of intervalued subset. To, develop the subset theory, Kongman et al. Redefined operation of the subsets to improve the several results, and a new decision-making method was considered by using this new operation. Please, definitions. Now come to the definitions. Next, next, yes, yes, some basic concept and definitions are described. You see, for this subset, let X be the universal set U and be the set of parameters. A is contained in E. Then Fx is the set of all fuzzy subset of X. Then F is called the fuzzy subset of X, where F is a mapping from A to Fx. And the example of this. And these are known as objects. These are known as parameters. And then FA, FE1, this C1, C2, this FE2, this is FA is for this subset over X to give the attractiveness of cars. This is an example of cars, and this is their parameters to select that attractiveness of cars. Yes, next, interval valued for the subset. In the same way, U be the universal set, E be the set of parameters, PU demonstrate the power set of interval valued set U, and A in the same way is contained in E. FA is called the interval valued for the subsets. And just see here, it is represented by the interval instead of one value. This is the difference. And then this both can be represented in the matrix form. Very simple. So this is can be, I will be taking as an example illustrating while you explaining the applications. Now there are other terms we shall be used oriented objects grade. For the fuzzy subsets, just like X, these are the objects, and this is a parameter. Uh, and grade with respect to parameters is given by grade qi is sigma j vij's divided by mod e, number how many of elements in e, where vij is the membership value of objects in fuzzy subsets. Yes, please, next. Yes, oriented parameter grade. So this is in the same way for the fuzzy subset. In the same way, EI is sigma EI divided by total number of objects. This is the so definition threshold value for the fuzzy subset. The C and E is the parameters. Threshold value is total sum of those values divided by x mod into E mod. That's number of x, number of A. This is known as threshold value. These are important concepts which shall be used in this. Okay, next. Yes, now application. The application of fuzzy soft matrix in a data dimension reduction is described using oriented object grade, oriented parameter grade, and threshold. Three things which I have defined will be used. So instead of using arithmetic mean, here calculating geometric means. Arithmetic means we, I and my one of the students have done work using arithmetic mean, and that paper will have you see the selected as the best paper of the World Academy out of 5,000 papers. So that's why I extended now the same by geometric mean approach. This is different and solution is good way. So algorithm of data dimension reduction, this is algorithm we shall be using input the subset HE and then construct soft matrix in subset. That's very simple. We can write in the form of the matrix that is known as soft matrix, soft set matrix actually. This is soft set matrix. Convert soft set matrix HE into the fuzzy soft set matrix. I shall let you know what is the process and find oriented object grade OI, parameter grade EI for each object and each parameter respectively using geometric mean. Find the threshold value T of fuzzy soft matrix using definition. Remove those rows for which OI is less than T threshold value and columns EI is greater than the T in fuzzy soft matrix. The new matrix is our desired dimension reduction matrix. Next, just see the example of, I will illustrate by the example. Let H11 be the set of 6 houses and the set of parameters are this 8 and let Mr. X is interested in buying a car on the basis of his choice of parameters given by this. Only this is a subset of, you understand, E, because that was 8, here is E1, E2, E3, E5 only. Matrix representation of subset H is given by. This is, we are giving 1 E5 in the first. This has been presented this. The presented all, this is the choices has been, you see, that's just like H1 will like all the 5, H2 will like only 4, H like that, H3, S4. In this way, we have been created a soft matrix. But this is soft matrix. Yes, next. And now we convert this soft matrix as P in the fuzzy matrix. What is that? That's the sum. 5, yes, 1, 1, 1, 5 divided by 5, 1. 4 divided by 5, 4 by 5. In the same way, this have been done. In the same way, columns also. And next, and fuzzy soft matrix, how to, you see, this is divide by them, multiply each every by RICJ. Bij is obtained by multiplying Ri Cj correspondingly. Okay, and you will be getting fuzzy soft matrix. Yes, next. Then next we determined Hi. This is product Bij's and and object grades like that. Multiply all this and take the fifth root. This you will get row. Firstly row, multiply row and then fifth grade. You see, when you will multiply, this will be non-zero value, otherwise other will be zeros, other will be zeros. So this we get. The same way we get this. Yes, next. Now, threshold value, which will be, as I explained in the algorithm, all the summation, take the values and divide by multiplication of the x mod and e mod and all this. We get, if we this, and then after, and that will come out to be decimal for 2. Now remove those values for which hi is less than ti and those columns for which ej is greater than ti. After removing, you get this. So this h1 and S6 HI is equal to this. Here it may noted that the data size was reduced only. Only these are the two value H1, H6 have approximately 80%, where our method is simpler than that of arithmetic mean due to Huda and Ritu. So this method is simpler than the arithmetic mean. So this is after removing corresponding rows and reduce for this automatic is represented in this table, and only instead of those values, 6 values, sorry, 6 values, only 2 values H1 are reduced. Others as no matter. They have no choice. Okay. Next. Now intervalued fuzzy soft matrix. Next, we discuss the interval valued soft matrix, and Meenakshi and Kaliraja have studied the application of this soft matrix in medical diagnosis, but there is a technique, our method is different. They have studied the other method. We have applied geometric mean interval valued function. It described and applied. Just like for the pair of fuzzy matrices, these have two matrices, A is less than if every value of this is less than that. So a algorithm for geometric mean method. Here we define an algorithm for application of intervalued fuzzy soft matrices in medical diagnosis following geometric mean method, which is different from method due to Meenakshi and Kalira. Geometric mean of interval valued fuzzy soft matrix is AL, AU is denoted by GA, and geometric mean A is given by this. We shall be finding what is AL, AU. I will be defining. Yes. Next. Yes, algorithm. Input the interval valued fuzzy soft matrix FD and its yes, complement over the set S of the symptoms, and D is the set of disease. S is a set of represent matrices FD and FC by relations R1 and R2 respectively. Input the interval valued fuzzy subset matrix Fs represented by relation matrix Q. Write the relation R1 and R in the form of AL and AU. I will let you know by the example how we take, and then we find the GMR1, GMR2, and GMQ respectively. Geometric mean already I have done in the previous case, because that reduces to the soft fuzzy soft matrix. I and then all the other things will be applied what have been applied earlier. Just see. Next, please. Yes. Now numerical example. it will be illustrated by the example that will be more clear. That's a only. Let us consider the set as the set of symptoms of certain disease. D is the set of disease. P the set of patients. Let S contain four symptoms, namely temperature S1, headache S2, cough S3, stomach pain S4. Let the possible diseases relating to the symptoms are viral fever and diseases are two, fever and malaria. D means and represented by D1 and D2. The approximate description of the medical knowledge of the record already in wherever you see there is a any department of medical or hospital, they have the medical knowledge on that of two diseases. Their symptoms is given by interval valued fuzzy soft set FD as like that. FD1 is S1.7 and 1. That's any value lying in between that. This is the S2 is in between this interval, closed interval, S3, S4. And FD2 in the same way, S1 like that. This interval valued for this subset FD and its complement F can be represented by the relation matrix R1 and R2 called the symptoms degree disease matrix and a non-symptoms disease matrix respectively. Matrix representative for R and R2 is next the C. We have represented them like that. D1, D2, R2, this is S1 and this is R2. Yes, next. We have to take their complement and yes, next. Yes, let P1, P2 be the set of patients. This is a set of patients and QS, the relation between the patient and symptom is given this. This is the relation. Matrix form of Q, QS is given this. That has been is a matrix form we have represented. Yes, next. Then R1L, this is we are to taking lower out of this D, which is lower, D1, D2, which is lower, in the same way R1U, which is higher, lower and higher. Okay, sorry, higher and what about in D2 higher? This is known as R1L, R1U, and this is ALAU. This is represented by AL. This is AL, just like AU is given as this. Yes, next. The same way R2L also, R2U, just like R1, this is R2. We have already two matrices R1, R2. This is about R2. This is lower and this is higher for that. Similarly, relation matrix Q form AL also. There also we have QL and QU. Here just like. Next. Yes, please. Yes, now we are to taking their method of multiplying AL of each AL and AU and taking under root. You will be getting this value. This is a calculation. Algorithm 4.1 as given below. We are applying this. And in the same way we shall be getting. Simply AL and AU multiply and take the under root that will give you the geometric mean. Yes, next. And the combining the relation matrices this separately with GMQ under the maximum minimum composition. This is a composition. We take the, you see, their maximum minimum GMQ with GMR1. T1 is equal to GMQ and GR2. Sorry, this is T2. T2 is GMQ, GMR2. So this comes out to be T1 and this will come out to be T2. Similarly, T3 is taken Q this And J minus GMR1. This is unit matrix I. This should be I or you see whatever J minus G. And in the same way, this is GMQ and minus GMR2, where J is the matrix with all entities I as given by 1. Yes. T3 and T4. The yes, please. Yes. Sorry. ST1. Back, please, back. Yes, back. Yes, T1. In the same way, similarly, T3 has been calculated and T4 has been calculated by take this value, matrix with all entities, J is unit matrix and like that. Then we getting T3, T4. Next. Yes. Now we take the diagnosis ST1, ST4 against the disease respectively. ST1 is maximum of T1, T4. T1 and T4, the maximum values are taken. You see the maximum values. And in the same way, maximum T2, T3, maximum values. And in the matrix form, ST and ST2 are written as, yes, next. Yes, ST1 will be getting this and this will be getting, this is the patient, these are the diseases. And then this is, subtract this to this, we get this and the maximum of that. What is maximum? First, second is the maximum. And in case of P2, second is greater. In case of P3, yes, D1 first is greater. From the above table, we see that patients, thus P1, P2 are suffering from disease D2. This is our conclusion that this D1, D2 are, sorry, P1, P2 patient are suffering with D2, while P3 patient is suffering with the D1. Suppose two values comes out to be equal, then in the same case it can be concluded that we arrive at the same result by geometry mean method as that of arithmetic mean method. But suppose both well, then we are to repeat the, you see, by taking other values or measuring the other values when they are repeated equal. Yes, next. So this is fuzzy soft set theory is being applied to many theoretical and practical fields. In present case, we define fuzzy soft matrix interval values which are matrix representation of fuzzy soft set and interval value fuzzy soft respectively. We apply fuzzy soft matrix data dimension reduction using this method and in interval valued fuzzy matrix in medical diagnosis by using the geometry mean method. The research finding can be further extended to intimistic fuzzy soft matrix and interval valued fuzzy soft matrix. This is open problem. If anybody is interested, they can take intimistic fuzzy soft matrix, interval valued fuzzy soft sets. Yes, next. These are the references. And in the end, I thanks again the organizers, particularly Dr. Felbin Kennedy, who has invited me and given this opportunity to be sharing my views with you. Thank you. Thank you, all of you.
Thank you, Professor, for that clear presentation. And in fact, you have given a very good future directions for our scholars to proceed in this area. Do we have any questions from the audience, participants?
Thank you.
Thank you, Professor. I now invite Dr. Sudhakar Chandran to present his talk on a proposal on fuzzy number supported AI 360 degree Student academic progress reporting system for Indian school education system. Over to you, sir.
Thank you, Doctor. Thank you, Dr. Dhanlakshmi. Thank you, Dr. Elvin, for giving me this chance. I think the video is available, right?
Yes, sir. You can see.
A proposal on FASI number supported AI 360-degree student academic progression reporting system for Indian education systems. So overall, any development of any nation depends on the four pillars, namely human resources, natural resources, infrastructure, and research and technological developments. This whole paper is having the idea of first, what is the need for this new assessment system, or I can call it as an observation system, review of the current assessment systems, and what is the role of fuzzy numbers in the assessment system, analysis of the current situations, and formulating the problem, and finally the concluding remarks. Okay, how it can be implemented and what are the challenges in that. So any development is built upon the four pillars. They are the human resources, natural resources, infrastructure, and research and technological developments. So these are the four very basic thing in any country, and that GDP and that overall growth is depending on how they are concentrating on the human resources. So the human resources, particularly employable resources, how to bring them to the employable level and how to make them to a standard of living. Overall, it shows that how the country is developed. More number of students are enrolled both in the formal academic system and in non-formal coaching systems. So the education has become more expensive, and in turn, progression to higher level is very low. So employable human resources from one level to another level, if they want to move, the cost of education is also very high for us. So due to the number of various factors, the unemployability rate is also increasing across the world. So it's very important to concentrate at this time what's going wrong and how to manage these resources effectively. Study shows that there is a great mismatch in the numbers between the educational qualification and the nature of jobs. If you see the successful people's, their educational qualification is something like BCom or BA, or even sometimes they are engineering qualified peoples. And when you compare their jobs, the job is not related to that. Sometimes they are working in the offices and sometimes they are working in the coffee shops. So when you think about what are the various reasons for that, so Indian National Education Policy 2020, which was recently approved by the Indian government, analyzed all these situations, and they came up with several factors, how to factorize them and how to resolve all these issues. So the National Educational Policy, they talked about very elaborative things about the reformation in the education system, right from the school to the higher education institutions, research education institutions, reforms in the structurals, reforms in the courses, reforms in terms of curriculum, and even the chairman, he talked about various types of arts to be included. So in his education, we are in his talk, we are able to analyze and understand that the government is very keen on this human resources, and they wanted to develop the human resources to utilize maximum for the national growth. So the aim of this paper is to find out the issues, what is stopping the progress. And fuzzy is uniqueness of any individuals are fuzzy in nature. Dr. Zade, he has given a very good insight on how it can be used, fuzzy numbers, and how we can capture the human thought to the fuzzy numbers, how we can convert it, and on how it can be embedded into the machine systems. And the latest developments of artificial intelligence are also getting the same idea, and they are using the same idea of incorporating them into the development of a nation. Processing of a large number of data and converting them into useful information can be done by an artificial intelligence decision-making support systems. Therefore, a fuzzy number AI 360-degree progress reporting system is suitable solution. When Dr. Ken Robinson was discussing, he clearly identified that our aptitude are highly personal. Okay, they can also be highly specific, not music in general. But he clearly specifies that the individual is different, and his talent is not categorized, cannot be categorized as a physics-oriented mind or chemistry-oriented mind or mathematics-oriented mind. He is very specific. It is not science. It is biochemistry. He is not a musician. He is a particular type of instrument specialist. Okay, each and every man is different. Okay, that's what he is categorizing that. Okay, understanding this factor, the government resources is also too much invested in that. Every country contributes the significant portions of the budget to improve the academic system and knowledge of their nations. The main four pillars of GDP are consumptions, investments, government spendings, and total exports. So for a common man perspective, education is the first step to get a job which can pay them to improve their economic status. Every parent wishes to put his or her ward in a school or college to get a certificate or degree. So companies are hiring the top class degree holders into their companies to improve their production and growth percentages. A survey showed that 65% of the parents spend their half of their take-home salary for their what's education. Extracurricular activities and other high significant, this is going to be a highly burden for the parents, and sometimes it is not reachable for the low privileged peoples. Education is highly expensive. So because of this reason, a great mismatch in the number between the educational qualification and employees and their job of nature. Survey states that the field of education by individuals and the states of nature have been very less relation. This was due to the tremendous change in the demand of job market, advancement in technology, and economic status imbalance in the society. India is rapidly growing in population, and the number of youth under the age of 25 are calculated as 600 millions in India. The youth under the age of 25 are calculated as 600 million in India. This is the census of 2018 data. Moreover, there is an addition of 46 new babies every minute added to the population. So everybody is not, the government is not able to support them job inside the country, and the other way is they are searching for jobs outside of the country. So this is the main reason for brain drain, what we call it as. So after investing a lot of money in the country, since they are not able to provide the job in the country, so the resources are utilized by the other nations. So population growth and the number of schools growth is not proportionate. population is growing higher than the number of schools available, and marketing is also one of the main reasons where very, very small schools are not able to survive. So this is the data. 43 new babies are added to the Indian population every minute. So statistics says that India needs to create 10 million new jobs every year. 10 million new jobs every year. This was considered as one of the main reasons for mismatch in the numbers between the achieved qualification and accepted job nature. And various types of talents are available in the children, which is not properly captured in the formal education system. In some places, it was captured by the school co-curricular activities or in the social environment system or in the media. So the literacy level of parents also important in some cases. However, it is limited only. Both the children and parents are not able to identify the natural talents and abilities. The reason is most of the assessments are based on the standard test prescribed by the NCERT or school boards. Across the country, there are 50 different school boards following the different curriculums. More than 50% of the schools follow the National Curriculum Framework, which was published by the NCERT in 2013. So human brains, their way of thinking and brain studies suggest that people are able to study properly when they are in their state of nature. When there is a lot of pressures provided to them, when their interest and the requirement of the job are varies very differently, and if there is an imbalance in the society, it creates pressure, and in turn, it is creating a adverse result in the growth of the country. Learning on the natural skills will be a pleasure event, whereas the learning becomes stressful if their natural talent is not related to the school curriculum. Many high-level achievers dropped their schools or higher education because it was not a peaceful or pleasant event for them. So several incidents are clearly registered in the literature that because of pressure, the peoples are not able to survive. Because of the pressure in the education system, they are not able to survive. On the other hand, the successful peoples are not having sometimes formal education, or sometimes they discontinue their higher educations and they concentrated more on their passion as a career. The standard curriculum and assessment treatment. The problem is the standard curriculum and assessment system treats the children as a homogeneous group, which is not true. Children's cognitive and other skills are not developing according to the chronological age also. They develop in different ages and in different domains. Theories hypothesis that cognitive development never stops even after 40 years. So it is clearly indicates that assessing the children's academic performance to their chronological age is not a correct method. The uniqueness of every children varies, and they are most unidentified by the existing academic system. Teachers and parents are having opportunities to identify them occasionally, but unfortunately they are not recorded and they are not converted into the useful information for the individuals. They are given with some certain amount of prizes or with the certificates, and after that they are pressurized in the regular education system. An interesting research done in Singapore school by Smith in 2017 shows that individual interest and their knowledge acquisitions are greatly related. The Finland education policy also agrees with that. So basically, our grading policies are can be categorized into two. One is commonly called as normalized norm reference system. The another one is a criterion reference system. So norm reference system, usually they consider the peoples and they take care of their top rankers only. And the low graders, they are ignored. And uh, uh, as a result, they are becoming the dropouts, and uh, their, their encouragement level has gone down. So in future, they became the unemployable human resources of any nation. So in addition to that, apart from this norm reference system and criterion reference system, some schools, they are following the hybrid systems. They follow partially the criterions and partially about the norm reference systems, and they try to encourage their talents in terms of curriculars and co-curriculars and try to bring them to the uh, employable resources for a nation. The main purpose of education is aimed to develop the individual's national talent and make use of them for the development of a country. The methods adopted, this method proposes a bottom to top approach in a step-by-step. This method adopts an approach from bottom to top. So instead of framing a curriculum and instead of framing a requirement at the national level and passing on to the students, so a system which can categorize and which can identify their talents and which can help them to enhance that, and based on the data, the nation can develop the different types of plans, and plans like Make in India and plans like other policies can be drafted so that it will become useful and it will become more successful for them as well.
Professor, we have another
Students are not, yeah. This method proposes to frame, to see the students in a 360 degree. The concept of 360 degree is the students are always around the society. The concept of 360 and Montessori system argues that learning happens with the peers more effectively. So the 360 degrees of a children are their parents, the society, the teachers, and then their peer classmates. So these are the four concepts we are taking. And these are the peoples constantly in touch with the children's. And this study and in this approach, we have taken concentrated on the school children only, particularly in the elementary level and lesser than that, whose ages are less than 12. So at present, the criterion reference system take care of what is the mark they are getting, and based on that criteria, whether they can be moved to the next level or not. So instead of that, this method proposes to take care of and capture all the data passed on by the children. So there are various types of data available in the schools, but unfortunately, these data are not captured for a long period of time. Only it was measured in the age of 12 or the grade of 12. In 1 year, they put them under a lot of pressure, and finally, the output is not a realistic one. So when you capture the data from level 1 or the grade 1 to the grade 12, and if there is a mechanism, so recording from the 4 various dimensions of the children. So from the parents, from the teachers, from the classmates, and from the immediate society experts. Okay, so the parents are having a lot of opportunities to observe the children's. They clearly identify that the children is having this talent, but because of the peer pressure and then comparison with their relatives and comparison with other factors, they pressurize them to go for the high earning jobs. So because if there is a mismatch between the requirement and their natural talent, finally the students are not able to perform well, and finally they lose their natural talent itself. So which is going to be a which gives a very drastic result for a nation. So how this can be captured and what are the methods it's proposed? So it can be captured in 4 ways. So at first level, the parents' input can be recorded in their proper system, and it can be transferred to the central data system, which can be monitored by something the newly educational policy proposal of PARAC. Then by using the data for observed over a period of time, we are able to identify what is the natural talent of the students. Once these data are collected over the nation, and for each and every student, it is, if they are maintaining the local experts input, the parents input, and their immediate society. In the immediate society, we are having a lot of experts available. Unfortunately, the school system is not using, the media is using, and some of the private systems they are using, and now they're calling it as a soft skills development and other new names, and they that's a another growing business in the industry now. So all these things, when the experts are available, the school system should incorporate them and put them in one particular place. And if the data are captured, and if it is centrally stored in a system, okay, like now we are having the central system for Aadhaar, and according to that, now we are having a Ministry of Education and NTA. So these organizations can maintain all these data, so that they will also know that what is the human resources, natural human resources available in the country. So the 360 observation proposal is first. So the national education policy concentrate more on the process, but it is not concentrating more on the assessment plans. Okay. So the 360-degree proposed that if the students are in the level QI, and if they are having the M independent scales RJ, okay, assume that the K number of experts are evaluating them. Assume that in the total system we are having R students. For every skill J at the level I, the observer's K's judgment on the student R can be captured as a fuzzy number denoted by Aij or K tilde. Okay, so this is the input can be captured from every school level, every teacher level, and it can be stored in the central systems. Then the other way around, the employee's requirement. So this is happening at various levels now. But for example, a student is finishing +2, we take care of the, if he's interested in engineering, we take care of only the maths, physics, chemistry marks. But if he's going for medical, we take care of, we count the marks of physics, chemistry, and biology only. So the employee's weightage of requirement is denoted by Pij. So this is the employee's requirement weightage, Pij. Pij is a crisp number which can be categorized as 20% or 30% like that. Now this data can be captured and converted into it can be captured in linguistic terms from the teachers and the local experts and the parents, and all these things can be converted into a fuzzy number. Okay, the fuzzy number matrix is Aij KR tilde. So this is a fuzzy observation matrix which can be monitored by the government or a central data center. Then whenever the employer requires, they have different requirements, different set of skills requirement, that is denoted by Pij. Now the employees can be given this data Mij available number of resources best suitable for their requirement. The skill total is given by this fuzzy matrix MJKR, which gives how many total peoples are available according to the skill. Then average fuzzy marks across experts. We have taken only 4 experts like parents and teachers, immediate society and the peers. Okay, this can be expanded as well, and it can be given different weightages as well. So the average fuzzy marks for a student is denoted by MJ or tilde. So this is going to be the very useful information in terms of fuzzy. Then for every student, according to the fuzzy skills, the weight is denoted by W or tilde. Now, the fuzzy set skill set can be ranked by using the score functions. Okay, so this is one of the score function we can use. Finally, the employer will get at any moment for their requirement how many peoples are immediately available. This will be a very good information for the peoples who are in the age of 25 or 30 who are aspiring for the jobs. Okay, so they will clearly come to know what is the job required after 5 years, what is the job or skill required after 5 years, what is the demand for them, so whether it is suiting for the natural talent or not. Okay, they will be able to analyze that. So this will create a lot of jobs for them. So the disadvantages is it's not easy to take this system to the remote villages, and where we are not able to get the experts for all the skills. There need a lot of policy changes from the government, and there is a need for technology to maintain them, which is safe, secure, and authenticated. So the overall 360-degree approach is a bottom to top approach. It's not the top to bottom approach. So studies also shows that, and we have done a pilot study in our classrooms and in our projects, and it shows that when they are in their natural talent, their performance is far better than what we are expecting. So thank you for Stella Maris College, Dr. Philbin Kennedy and the team of peoples for giving me this opportunity. And I thank Middle East College for giving me this offer. So this is the overall proposal from our side, but still it needs a lot of study in future. Thank you.
Thank you, Professor. I would like to make a remark or a comment over here. In the present pandemic situation, the entire education system in India has totally changed, and we have moved on to the technological or the online teaching and learning method. But all of us are aware that most of the students and schools and colleges are facing a lot of issues with respect to the economical and the social background of the students of a country. And henceforth, we are not able to really provide them with the necessary education through this system. Therefore, my remark is with respect to education in our country, since this talk is about the Indian school education system, the entire system can be changed only when the socio-economic system of the country changes to a certain extent in order to provide them with the basic technological study as such. This is just my remark, which I would like to comment at this moment.
Yeah, I agree with you. That's what I told you in the beginning itself. Survey states that 64% of the population, they are spending 50% of the money already. The 50% of their take-home salary is not coming to the formal system. That is that's what our concern is. So, for example, the government is offering the free education, but people are not ready to go there, and they are going to take it in the private institutions. And from the private institutions, they are going for co-curricular activities to different places. And from there, they are moving to the online educations, or what we can call it as the extra entrance coaching classes, something like that. So they are spending the money, but it is not at the formal education system. So once the government take care of, And if they are ready to give everything at one place, that's what our concern. Within the 8 hours of time, if they are able to provide everything, so we are giving a lot of contents which is not required for them. For example, we are teaching mathematics for a student to the large extent, which he is not going to use it after becoming a surgeon. Differentiation and integration, but it's an example. But we are teaching it every day 2 hours, every day 3 hours for them, right from the to certain extent to up to 5th level or 6th level, it's okay. But after that, after 5 years, we are creating a what you can call it as unusable human resources out of the cost of the public. So the National Education Policy has 2020 has given a lot of good proposals, proposals, and the assessment systems also, they allow us to go and take the modules or take the courses, but it is in the hand of the local experts, particularly the teachers and the school authorities, to guide them. So our proposal is that once you are bringing everything into the assessment system, not insisting all the 5 curriculum based. I agree with you, the teachers are not having 100% autonomy, or the school management is not having 100% autonomy over there at present. But within that limit, if anything is possible to do that, that can give a tremendous change in the education system. Thank you. Thank you for your feedback.
Thank you, sir. I would like to check whether Dr. Prasun Kumar Naik has joined the session. Sir, may I know whether you are there in this?
Thank you, madam.
Thank you, sir. Okay. Thank you, sir, for your nice presentation. We now have the next resource person, Dr. V. Dhanalakshmi, Assistant Professor, Department of Mathematics, and Contact Person, FIM 28, SCM, SPS 2020. It's my privilege to introduce Dr. Dhanalakshmi, who has completed her undergraduation in WCC, post-graduation in Stella Maris College, her MPhil from Ramanujam Institute of Advanced Study in Mathematics. She pursued her PhD in fuzzy mathematics in Stella Maris College under the able guidance of Dr. Felbin C. Kennedy. She has around 17 years of teaching experience. She has participated in several national and international conferences, seminars, and workshops, and has published 8 research papers in international peer-reviewed journals. Her passion towards technique and technology has motivated her to be upgraded and updated with the latest gadgets and technology in the system. Thank you, Professor, for sharing your expertise with us. I now invite you to present your talk on characterization of linear fuzzy numbers. Over to Dr. V. Dhanalakshmi.
Thank you, ma'am. Thank you for those nice words. So let me share my screen. Okay. So my topic today is characterization of linear fuzzy numbers. So as we all know, uh, the situation, that is the problem where we have uncertain data or imprecise or vague data, it is important to model it as a fuzzy sets or fuzzy numbers. So while we model, most of the problems we come across as triangular and trapezoidal, that is piecewise linear membership functions. But still not all the cases can be modeled as a linear membership functions. So there are lots of research in nonlinear fuzzy numbers. But again, when using nonlinear fuzzy numbers, we come across some computational difficulties. So, and as Professor Ganesan in his speech mentioned, that triangular fuzzy number can be conveniently represented as a triplet, right? So similarly, we have seen that in many cases, the trapezoidal fuzzy number is denoted as a four tuple, where it is easy for us to define the arithmetic operation, and it is computationally simpler than working with the membership functions and proceeding it. So in this talk, we are going to see how any fuzzy number can be approximated to a linear fuzzy number so that this component-wise representation can be used. So let me skip this. So the basic definition of fuzzy sets and fuzzy number. So of course, a fuzzy number is a fuzzy set with a universal set of real numbers with the condition that the membership function is convex, normal, and piecewise continuous. So here we define linear fuzzy numbers as the one whose membership function is piecewise linear. So as I mentioned, the very famous triangular and trapezoidal fuzzy numbers are the examples. So now we have proved a theorem in which any fuzzy number with bounded support can be approximated to a linear fuzzy number. So let me give an outline of the proof. So the given fuzzy number, there is any fuzzy number, it could be any nonlinear, like many problems are also modeled as a quadratic fuzzy number, exponential, or a Gaussian fuzzy number. So any fuzzy number we can consider, and whenever we have a membership function, we can always write the alpha cut for it. So we can have the alpha cut for the fuzzy number. So now we will approximate it to a linear fuzzy number. Okay. So the linear fuzzy number a 2n plus 1, that is we will have 2n plus, sorry, 2n plus 2. So we will have this linear fuzzy number with 2n plus 2 entries, that is components in it. So which means we are going to split our left hand side into n plus 1 parts and the right hand side into n plus 1 parts. Okay, so the alpha, the alpha levels. Okay, so we will divide our entire alpha into n plus 1 parts with I ranging from 0, 1 to n. And similarly, the right hand side, we will come down from 1 to 0. Okay, so the correspondingly, we are defining the points. So we will have the alpha cut of this approximated linear fuzzy number to be this. Okay, I'm sorry for the distraction. So the alpha cut of this approximated fuzzy number can be computed in this way. So now we have the alpha cut of the given fuzzy number and the alpha cut of the approximated linear fuzzy number. So we can compare them. So for comparison, I'm using this distance function, which is defined in terms of the left and right spreads. So, and then we find that the and then we find the distance between the fuzzy number and its linear fuzzy number to be this, which is approaching to 0 as n tends to infinity. So of course, as we take more and more points, they both will coincide, right? So, but we cannot go on for an infinite number of points, but we can decide on some value, some epsilon, and we can stop with that. Whichever is computationally okay for us to do, we can proceed. Okay, so just a simple illustration of this, whatever we have seen in this theorem. So assume that we have a quadratic fuzzy number. We are defining its alpha cut, and then um, we can define the components, the left side components, as I mentioned, that n plus 1 points in the left side and the n plus 1 points in the right side can be defined. And then for n equal to 2, which means 2n plus 2, we should be having 6 components. So we'll be getting this value, that is, as how in a triangular fuzzy number, we'll be having 3 components. So here we are having 6. So to visualize how this is, so the curve plotted in the red is the given quadratic fuzzy number, and for n equal to 2, so this is the linear fuzzy number that is approximated. So in case if instead of n equal to 2, if I give n equal to 1, we get this. So even though there are 4 points, there is 4 components, it is still a triangular fuzzy number. So we see that these two values are the same. As I mentioned, as we keep on increasing the n value, your linear fuzzy number becomes much more closer to the given fuzzy number. Say for n equal to 12, it is much more the same. And this is another example for the exponential fuzzy number. So yeah, for various n values. Okay, so now coming back to the benefits of defining the fuzzy number, that is approximating it to a linear fuzzy number. So we can represent our fuzzy number in terms of the components. That is, if we are fixing it as n, okay, so for some n, then we'll be just dealing with the n numbers instead of the membership function. It'll be just the n numbers, and the addition and scalar multiplication can be defined in terms of the components. And we have also proved that this is same as the one which we do with the extension principle. And also we find that the addition and the scalar multiplication by a non-negative scalars form a convex cone. So which means the set of fuzzy numbers, the linear fuzzy numbers, form a convex cone in Rn. So this is what I mentioned. And we can define the general definition of the dual and polar cone goes in this way, and it is derived for LFN to be LFN star. The dual cone will have the points in Rn whose sum of the components is non-negative, and for the polar cone, the sum of the components will be less than or equal to 0. Okay, then we can define the projection operator. So which means we define a mapping which takes any point of Rn to a point in the LFN. Okay, so it is defined as the distance between the x, and it is defined to be the infimum of the distance between x and its projection y tilde. And we have proved some of the properties that this projection operator satisfies. So I'm not presenting the proofs of these, but the thing is, when we derive that this, when we find that these properties are satisfied, at one point we could prove that the point y tilde x in LFN is a projection of the point x in Rn if and only if yx is, of course, this belongs to LFN, and z tilde, which is defined as y minus x, should belong to the dual cone LFN, and the z and yx should be orthogonal. Okay, the reason why I have repeated this y tilde x in LFN is this is nothing but the linear complementarity problem. So which means for finding, that is, you can reformulate your problem of projection of any point of Rn in LFN is now formulated as a linear complementarity problem. So for which there are many solution methods available which we can use. Okay, and there are few more results that we have developed, discussed, derived on this projection and on this LFN. So one thing is for x bar in Rn, that is any point in Rn can be decomposed into a point of LFN plus a point in LFN star, that is its dual cone. And some more properties of the projection operator, like idempotent, then it is additive, and whenever this P is a projection operator onto LFN, then I minus P, I is the identity mapping, I minus P becomes a projection operator of Rn onto LFN. Okay, the next thing is, since we have identified our linear fuzzy number as the collection of linear fuzzy number as a cone, we could also define a matrix A which will have 1, in the diagonal and the upper diagonal matrix. And for that matrix A, the set A Rn plus is exactly the LFN. So which means we are able to say that the convex cone LFN is a simplicial cone. So as I mentioned, so with all these properties derived, we could say that is we could reformulate our projection operator as a linear complementarity problem. So, and of course, we have identified that is we have re-returned the problem that y minus x was the one mentioned in the few slides before. But now it is also, since we are able to derive it as a simplicial cone, we could write it in terms of the matrix A. So now this can be applied in various things. Like one simple application of this is the subtraction of fuzzy numbers. So we know that subtraction is not that easy or not that direct as how we do with the addition. And in many ways, ways that we define our subtraction, we see that the spread increases. Okay, so of course for addition also the spread increases, but subtraction also again the spread increases. So here the one application is we can do a component wise subtraction that will not be a point in LFN, but it will be a point in Rn, which can always be projected to an LFN. Okay, so these are some of the references that I have used.
Thank you, Professor Dhanlakshmi, for your lucid presentation. Can we have a couple of questions from the participants? Okay, thank you, ma'am. So we have come to the end of the symposium, and we now move on to the paper presentation. May I now request Dr. Sudhagar Chandran to chair paper presentations. Over to you, sir.
Thank you, madam. Shall we start, or is there any break for them?
Yes, sir. You can invite them to present, sir.
Yeah. The first presentation is a consideration about rough sets, the Prairie algorithm, ensemble learning, and the rule-based functionality for the enable AI. I request the author to start. The author is available.
You're not audible.
I'm waiting for the author.
I think the author Binu is there. She's there.
Yes, ma'am, but this is not the paper which I need to present, ma'am. My paper was on transportation problem, ma'am. The topic, sir, good evening, sir. The topic, what you have read is different from what I'm presenting, sir.
Okay, but the link shared with me is this one. I don't have any.
Okay, shall I proceed with my topic, sir? I'm Binu.
Can someone
yeah.
someone help me from the...
It's actually submission number 7, transportation problem with heptagonal intuitionistic fuzzy number and nanogonal intuitionistic fuzzy number solved using ambiguity index. Am I right?
Yes, ma'am. That is the paper, ma'am.
Yes, this is the paper sheet.
But I am having another 4 papers: fuzzy set theory, axial angles, representation. Okay, could you please send me the recent list? Yes, Mr. Binu.
Yes, sir. I'll send
please
it
go
now,
ahead.
sir.
Please go ahead.
Good evening, sir. Shall I go ahead, sir?
Yeah, please go ahead, please.
Yes, sir. Sir, am I audible and my slide is visible, sir?
Yeah.
Yes, sir. Good evening to one and all present here. I am VP Binu, Research Scholar, under the guidance of Dr. V. Kamal Nazir, Associate Professor, Department of Mathematics, the New College, Chennai. I am here to present on the topic, transportation problem with heptagonal intuitionistic fuzzy number and nanogonal intuitionistic fuzzy number solved using ambiguity index. Just a moment, sir. I'm just trying to move my slide. Okay. Okay.
No, it's fine.
Yes. The abstract, the paper deals with a new ranking technique to solve the transportation problem in an intuitionistic fuzzy environment. The cost, demand, supply of the transportation problem are heptagonal intuitionistic fuzzy number and nanogonal intuitionistic fuzzy number with the membership and degree of membership and degree of non-membership. The validity of the proposed method is illustrated with 2 different examples involving unbalanced transportation problem with nanogonal intuitionistic fuzzy number and a transportation problem for profit maximization with an heptagonal intuitionistic fuzzy number. The keywords are intuitionistic fuzzy number, heptagonal and nanogonal intuitionistic fuzzy number, value index, ambiguity index, alpha cut, and beta cut. Preliminaries. Let X be an universal set. An intuitionistic fuzzy set X is defined as a collection of all X which has a membership function and a non-membership function, both ranging from X to closed interval 0, 1. This defined degree of membership and non-membership satisfies the condition 0 less than or equal to mu a tilde of X plus b a tilde of X, which is less than or equal to 1. Here I have defined the membership and non-membership function of an heptagonal intuitionistic fuzzy number, followed by a membership function of a nanogonal intuitionistic fuzzy number, and then I have a non-membership function of the nanogonal intuitionistic fuzzy number. The maximum degree of membership, WA tilde, and the minimum degree of membership, UA tilde, satisfy the conditions 0 less than or equal to WA tilde less than or equal to 1, and 0 less than or equal to UA tilde less than or equal to 1, along with the condition 0 less than or equal to WA tilde plus UA tilde, which is less than or equal to 1. The parameters reflects the confidence level and the non-confidence level of the intuitionistic fuzzy number. These are the alpha cuts of the heptagonal intuitionistic fuzzy number and the beta cut of the heptagonal intuitionistic fuzzy number. We have the alpha cut and the beta cut of the nanogonal intuitionistic fuzzy number, which are calculated as below. The ranking is based on value and ambiguity index, the value of the membership functions and the values of the non-membership function. The value of the membership function ranges from 0 to WA tilde with the average of the left alpha and the right alpha cut and F into multiplied with respect to F of alpha D alpha. And the value of the non-membership function is a interval which ranges from UA tilde to 1. L A tilde I of beta plus R A tilde of beta divided by 2 G of beta D beta. Throughout the paper, I have chosen F of alpha to be 2 alpha divided by WA tilde where alpha belongs to a closed interval 0, comma WA tilde, and G of beta is taken to be 2 times of 1 minus beta divided by 1 minus UA tilde, where beta belongs to UA tilde, comma 1. These are the value of the membership functions and the value of the non-membership functions of a heptagonal intuitive fuzzy number, which are calculated with respect to the alpha and beta cut, followed by the value of the membership and value of the non-membership function of the nanogonal intuitive fuzzy number. Then we have alpha cut and beta cut of an ambiguity index, where the ambiguity index is defined as an interval from 0 to WA tilde, RA tilde of alpha minus LA tilde I of alpha, F of alpha, D alpha. And the non-membership function of an ambiguity index ranges from UA tilde to 1, RA tilde of beta minus LA tilde of beta, that is right minus the left cosets of G of beta, D beta. Here, f of alpha and g of beta takes the same value, and the ambiguity of the membership function with respect to the heptagonal intuitive fuzzy number, the ambiguity of the non-membership function with respect to the heptagonal intuitive fuzzy number are calculated, and followed by the nanogonal intuitive fuzzy number, ambiguity with respect to membership function and non-membership function, all of which satisfies the condition 0 less than or equal to WA tilde plus UA tilde, which is less than or equal to 1. It is such that the membership of the ambiguity of a fuzzy number is always greater than or, greater than or equal to the, non-membership is always greater than or equal to the membership of the fuzzy number. Here is the ranking technique, which involves the sum of the value and ambiguity. We have an algorithm how to solve and how to get the initial basic feasible solution by intuitive fuzzy Ogle's approximation method with respect to the heptagonal intuitive fuzzy balanced transportation problem, followed by an algorithm for the nanogonal intuitive unbalanced transportation problem. The proposed ranking technique is used to convert the given fuzzy number to a crisp number. We have a modified distribution optimal solution by the intuitive fuzzy Ogle's approximation method for intuitive fuzzy balanced transportation problem. This is an illustrative example which involves an heptagonal intuitive fuzzy number with the maximum degree of membership is 0.6 and a minimum degree of membership is 0.2, for which the proposed ranking method is applied and the values are converted to crisp values. The crisp values are then proceeded with the transportation problem, which leads to the allocation and then which leads to the total profit of 3,911. Followed by an illustrative example of a nanogonal intuitive fuzzy number where the maximum degree of membership is taken to be 0.7 and a minimum degree of non-membership is illustrated as 0.2. The applied ranking method, the proposed ranking method is applied to convert the fuzzy numbers to crisp values. The table gives the crisp values of the nanogonal intuitive fuzzy number. The VAM method is applied. The allocations are calculated, proceeded by the VAM method, and then the modified distribution method to find the optimal solution. And this leads to the total cost of 356 rupees. Comparatively, this method yields, the cost method yields less cost when compared to the Russell's method, which has already been worked. To come to the conclusion that this method helps to find the optimal solution in intuitive fuzzy environment, which is used to propose using value and ambiguity for nanogonal intuitive fuzzy unbalanced transportation problem and a heptagonal intuitive for maximizing transportation problem. Value and ambiguity ranking method is used to solve the intuitive Ogle's approximation method to find the initial basic feasible solution and then modify distribution method for optimal solution for the intuitive fuzzy transportation problem. And these are my references. So,
yeah, thank you.
Yes, sir.
Any questions? Any questions from the participants?
Yes, sir.
Could you please go to the conclusion part?
Yes, sir. Yes, sir.
Is there any other method you applied other than Ogle's approximation method? Because the last step you are deriving to the crisp matrix only. Right?
Yes, sir. Yes, sir. No, yeah. I have applied only Ogle's approximation method, sir. I have not applied a northwest corner rule or any other method for the basic feasible solution, sir.
You never tried, right?
I have tried, sir, but Ogle gives me more, more approximate value compared to the northwest corner rule and other least cost entry and row and column maxima minima methods, sir.
Okay, thank you.
Thank you, sir. Thank you, sir. Shall I stop?
Thank you, Ms. Bina.
Thank you, sir. Thank you.
Yes. The next paper
Gave
is
you another list.
I saw from the
Yes.
program list.
Yeah.
The list given in the program and sent to me the mail. There is a discrepancy.
Yeah,
no
that's
problem.
why
I note down from that.
Okay.
Can I call upon Preeti Jennifer, Amalra Armika for presenting the papers on ranking of linear octagonal intuitionistic fuzzy numbers using a value index and an ambiguity index with an application to fully fuzzy transportation problems.
So, can you hear me?
Yeah.
I'm Amalora Arumika.
Yeah, please. We are happy to have you here in the conference.
Thank you, sir.
You can start presenting.
Yes. Is my screen visible, sir?
Yeah, everything is perfect. Screen is visible and you are clearly audible. Please start.
Good evening to one and all present here. I'm Amalora Arumika, pursuing my research under the guidance and supervision of Dr. Feldin C. Kennedy. And the title of my presentation is Ranking of Linear Octagonal Intuitionistic Fuzzy Numbers using a Value Index and an Ambiguity Index with an application to fully fuzzy transportation problem. It is somewhat similar to the previous presenter. And the outline of my presentation goes like this. First, we'll start with my introduction, then basic definitions, then we'll define our proposed ranking method, then the problem description, an algorithm is given, and a numerical example to illustrate the algorithm and the results and references. Introduction. Fuzzy numbers play a vital role in many real-life problems where uncertainty persists. We have considered one such type of fuzzy numbers, and we have defined one such type of fuzzy numbers called octagonal fuzzy numbers by one of the authors. And in this paper, we have considered a linear octagonal intuitionistic fuzzy numbers defined by Dr. P. Rajarajeshwari and G. Menaka in 2017. Ranking techniques, well-defined ranking techniques are useful to compare and order any fuzzy numbers, which will have an effect in finding the optimal solution in several applications. In this paper, we introduce a well-defined ranking procedure using value and ambiguity indices. Using these indices, ranking is proposed, and which yields better results than the existing methods. The definition of a linear octagonal intuitionistic fuzzy number is given here. This is the membership function, and this is the non-membership function. And the diagrammatic representation is shown here, membership function and non-membership function. Then we recall the alpha cuts and beta cuts of the linear octagonal intuitionistic fuzzy number. The alpha cuts are given here and the beta cuts are given here. Any two linear octagonal fuzzy numbers are compared using the ranking shown here. And we also recall the arithmetic operations of linear octagonal intuitionistic fuzzy numbers. Sorry, linear octagonal. In this paper, we have defined a new ranking technique with value and ambiguity indices for both membership and non-membership functions of intuitionistic octagonal fuzzy numbers. So we define the value to be the value of the membership function to be the sum of the alpha cuts of the membership function. We observe that by giving different weights to elements in different alpha cut sets, the function diminishes the contribution of the lower alpha cut sets, since these cut sets arise from the values of mu of A tilde have a considerable amount of uncertainty. Then the derivation of the value of the membership function is shown here, and the computation value of the membership function is shown. Similarly, we define the value of the non-membership function of linear octagonal fuzzy numbers as the sum of the beta cuts as the sum of the beta cuts. Similarly, the effect of weighting on different beta cut sets and G of beta diminishes the contribution. Then these cut sets arise from the values, so it also has a considerable amount of uncertainty. Then the derivation of the values of non-membership function is shown here, and this is the final value. Similarly, we define the ambiguity of the membership function of linear octagonal intuitionistic fuzzy numbers as the difference of the membership functions. And similarly, here also the global spreads of the membership function basically measure how much vagueness is there in the linear octagonal intuitionistic fuzzy numbers, and the derivation is shown similarly. This is the ambiguity of the membership function, ambiguity of the non-membership function. And the final computation is shown here. Using these value and ambiguity indices, ambiguity values, we also define the value and ambiguity index of the linear octagonal intuitionistic fuzzy numbers as shown here, where lambda belongs to 0, 1. This lambda plays a vital role. We can choose lambda according to the suitability of the subject, and lambda belongs to 0, 1 by 2, 1.5, 0.5 indicates decision makers' pessimistic attitude towards the uncertainty. And also when lambda belongs to 0.5, 1 indicates decision makers' optimistic attitude towards uncertainty, and lambda equal to 0.5 shows the neutral value. So when lambda is 0.5, the computational results are here, and the final ranking is shown here, and this is the ranking we used. So to understand this, we have given an example here. Let A and B be two linear octagonal intuitionistic fuzzy numbers, and using k is equal to this is k is equal to 0.3. Using k equal to 0.3, we have found out the value of the membership, value of the non-membership, ambiguity of the membership, ambiguity of the non-membership functions. And we also find the value and ambiguity indices using lambda equal to 0.3 and lambda is equal to 0.5. We can observe that the value index is maximized and the ambiguity index is minimized. Thus, while comparing the indices of two linear octagonal intuitionistic fuzzy numbers, we observe that when the result wanted to be optimistic towards uncertainty, we can choose lambda equal to 0.5. So in the example, we have taken lambda to be 0.5. Now, this is the procedure for ranking intuitionistic octagonal fuzzy numbers. First, we compute the value and ambiguity indices of the membership and non-membership, then the value and ambiguity indices, then the rank. Then we have considered a transportation problem. As everyone knows, transportation problem's objective is to consist in minimizing the transportation cost of a given commodity from a number of sources to a number of destinations. Uncertainties such as inflation, fuel prices, economic conditions, employment levels, flu, natural events in the problem have received less attention due to its complexity. These uncertainties cause changes in the cost of activities, and also the total cost of the project may differ significantly. It's the mathematical formulation of a linear octagonal intuitionistic fuzzy transportation problem, where all the values are linear octagonal intuitionistic fuzzy numbers. It's the necessary and sufficient condition. We have considered the algorithm defined in Phi by one of the authors. This algorithm yields best results because this algorithm is given for a fully fuzzy transportation problem, and we have solved the problem, the given example, without converting to crisp using this algorithm. So this is the algorithm given by one of the authors. So I'll just skip. So numerical example, we consider the linear octagonal intuitionistic fuzzy transportation problem. The table below displays an individual cost of transporting a piece of bag from the associated supply center to the various demand destinations. The cost, demand, and sources are represented using linear octagonal intuitionistic fuzzy numbers, the demands and supply. So we use the proposed algorithm by one of the authors, and we have solved, and I've tabulated the computation values alone. So the problem is not balanced. First, I have balanced the given transportation problem. Then by using the fuzzy 0-point method in the algorithm, we have the following final allotment table. After cancellation, we have got this. And using the allotment rules of the fuzzy 0-point method, we have got the final allotment. Therefore, the fuzzy optimal solution for the given fuzzy transportation problem is tabulated here. And the fuzzy optimal value is given here, which is defussified with our ranking technique proposed is 4.63, which is much less than the crisp solution. And we have also compared with trapezoidal fuzzy numbers, linear intuitionistic fuzzy numbers. That also is less when compared to the octagonal intuitionistic fuzzy numbers. These are my references. Thank you, sir.
Thank you, ma'am. It was really very interesting. One thing I would like to know is how did you use any softwares for calculation of these ranks?
Yes, sir. I have used MathCAD.
Okay. Did you have you given the code in the full paper?
Sir?
Have you given the code in the full paper?
No, sir.
Okay, fine.
I will give. Not yet submitted my paper.
Okay, fine. I suggest you to go, maybe you can try it in the coded softwares. I think
Yes, sir.
is only user interface, right?
Yeah, yeah. Just for computation I've used.
Okay.
I'm planning to write a program in MATLAB also, sir.
Yeah, that will be good. That will be good extension, and
that will be easier also, sir. Yeah.
No, that can be converted into another paper, or it can be applied for some applications which can be published as a separate paper for you. Okay, so make sure that the accuracy level is also improving. Thank you. Thank you, ma'am, for your wonderful presentation.
Thank you, sir.
The next paper is single-valued linear octagonal neurons of numbers and its applications to multi-attribute decision-making problems. May I invite the author, Subhashri?
Hello, sir.
Yeah.
Am I audible?
Yes, yeah, you are audible, ma'am.
Okay. Can I share my screen, sir?
Yeah, you can go ahead, please.
I'm Subhashri, doing MPhil in Mathematics at Chelameres College. And the topic I'm going to present is single-value linear octagonal neurosophic numbers and its application to multi-attribute decision-making problems. And this work is done jointly with the research scholar Arul Rosat Marlinez, Department of Mathematics, Chelameres College, and research supervisor Dr. Philbin C. Kennedy, Associate Professor, Department of Mathematics, Chelameres College. In order to make a definition of single value linear octagonal neurosophic number, we need basic definitions like a single value neurosophic set, single value neurosophic number, and linear octagonal neurosophic number. Sorry, linear octagonal fuzzy number. Linear single value neurosophic set definition goes like this. Suppose if we take X to be our universal set and we define a single value neurosophic set A tilde as a set which is characterized by truth membership function, indeterminacy membership function, and falsity membership function. And these three functions belongs to the unit interval 0, 1. And we represent single valued neurosophic set as given here. Moving on to single value neurosophic number, in order to qualify a single value neurosophic set A tilde as a single value neurosophic number, it has to satisfy the given four conditions. If it's satisfied, then we call A tilde to be single value neurosophic number. Linear octagonal fuzzy number, which was put forth by Malini ma'am and Dr. Philbin C. Kennedy, is defined as a fuzzy number which is denoted by A1, A2, etc. up to A8, K, where K lies between 0 and 1. And these A1, A2, etc. up to A8 are real numbers whose membership function is given as follows. And the diagrammatic representation of this is given when K is equal to 0.5. Now we define single value linear octagonal neurosophic number, which is shortly written as SVLONN. And it is defined as a set A tilde is equal to set of all X with the membership, truth membership function, indeterminacy membership function, and falsity membership function for each X belonging to capital X in the set of real numbers R. And their truth membership function, indeterminacy membership function, and falsity membership functions are given as follows. And the diagrammatic representation of SVLONN is given for k is equal to 0.5. And we represent SVLONN of A tilde is equal to A11, A21, A31, etc. up to A81, B11, B21, etc. up to B81, C11, C21, etc. up to C81, comma K. And in order to find the observations, we have taken k is equal to 0 and k is equal to 1 in the definition of SVLONN, and the following observations are made. In order to calculate the cuts of SVLONN, we are going to first calculate the alpha cut. For that, we are going to consider A tilde to be SVLONN. And an alpha cut of A tilde is defined as a crisp subset of R, which is given by alpha cut of A tilde is equal to set of all X such that truth membership function of X is greater than or equal to alpha, where alpha lies between 0 and 1. And we calculate alpha cut of A tilde in two cases. One is for alpha belonging to closed interval 0, k, and alpha belonging to the interval opened at k and closed at 1. Similarly, we calculate beta cut of A tilde, and we define beta cut of A tilde to be a crisp subset of R, which is given by beta cut of A tilde is equal to set of all X such that IA tilde of X is less than or equal to beta, where beta lies between 0 and 1. And for this also, we have done beta cut of A tilde in two cases. One is for closed interval 0, k, and one is for interval opened at k and closed at 1. And similarly, we have defined gamma cut of A tilde. By using these three cuts, we can define alpha, beta, gamma cut of A tilde, and which is again for two cases. And moving on to arithmetic operations on SVLONN, the first arithmetic operation we have done is based upon extension principle. For that, we have considered star to be our arithmetic operation and A tilde and B tilde to be two SVLONN. And we have considered x1 and x2 as our input vector, and we have considered y to be our output vector. And the definition of A tilde star B tilde of y as is follows. And the next is based upon alpha, beta, gamma cut, and the results are mentioned here. The first result is about the addition of two single value linear octagonal neurosophic numbers A tilde and B tilde, and which equals A11 plus A12, etc., A81 plus A82, B11 plus B12, etc., B81 plus B82, C11 plus C12, etc., C81 plus C82, K. And the next result is about the scalar multiplication of A tilde with a real number R. And this case, and the result is given for two cases. One is for R greater than 0 and one is for R less than 0. And the definition of RA tilde goes like this. Moving on to value for SVLONN. In order to define value for SVLONN, we are going to consider alpha cut, beta cut, gamma cut of a single value linear octagonal neurosophic number A tilde. Then we are able to find the value of truth membership function, indeterminacy membership function, and falsity membership function by using the equations 1, 2, and 3. And the different weighing functions that we have used in 1, 2, 3, that is namely f of alpha, g of beta, and h of gamma, can be set according to the nature of the decision making. When we take f of alpha is equal to alpha, then it gives rise to different weights to elements in different alpha cuts. Similarly, when we take g of beta is equal to 1 minus beta and h of gamma is equal to 1 minus gamma, then they also give different weights to different beta cuts. And then we can calculate the value for truth membership function by taking f of alpha is equal to alpha in v of A tilde. And similarly, we can calculate value for indeterminacy membership function by taking g of beta is equal to 1 minus beta in vi of A tilde. And finally, we can calculate the value for falsity membership function by taking g of gamma is equal to 1 minus gamma in vf of A tilde. Moving on to ambiguity for SVLONN, as we considered alpha cut, beta cut, gamma cut, in order to define value, we are going to consider the same for defining ambiguity. And then we can calculate the ambiguity of truth membership function, indeterminacy membership function, and falsity membership function of A tilde by the equations 4, 5, and 6. When we look into the equations 4, 5, and 6, we are able to see that R alpha of A tilde minus L alpha of A tilde, and R beta of A tilde minus L beta of A tilde, R gamma of A tilde minus L gamma of A tilde are nothing but the length of the intervals of alpha cut of A tilde, beta cut of A tilde, and gamma cut of A tilde. And these three membership function will help us to determine the vagueness of A tilde. And moving on to ambiguity for truth membership function, we can calculate the ambiguity for truth membership function by taking f of alpha is equal to alpha in at of A tilde. Similarly, we can calculate ai of A tilde by taking g of beta is equal to 1 minus beta. And we can calculate af of A tilde by taking h of gamma is equal to 1 minus gamma. And since we have the value of a truth membership function, indeterminacy membership function, and falsity membership function, now we can define value index for A tilde. And it is defined as value index of A tilde is equal to lambda times Vt plus mu times Vi plus gamma times Vf. And the ambiguity index of A tilde can be defined as ambiguity index of A tilde is equal to lambda times At plus mu times Ai plus gamma times Af. The coefficients that we used in defining value index and ambiguity index express the decision maker's preference with the condition that lambda plus mu plus gamma is equal to 1. And the value index and ambiguity index will reflect the decision maker's attitude towards SVLONN. And this theorem is based upon the value index, and it is stated that if we have two single value linear octagonal neurosophic numbers A1 tilde and A2 tilde, and if we have lambda, mu, gamma belonging to closed interval 0, 1 and phi belonging to the real number, then value index of A1 tilde plus A2 tilde is equal to value index of A1 tilde plus value index of A2 tilde, and value index of phi of A1 tilde is equal to phi of value index of A1 tilde. Similarly, we have the result for ambiguity index. In order to rank the two considered A1 tilde and A2 tilde of a single value linear octagonal neurosophic numbers, by using the value index and ambiguity index, the following procedure is used in ranking them. And this is a theorem which is based upon the proposition, that is, let A1 tilde and A2 tilde, A3 tilde be 3 SVLONN. Then if A1 tilde is greater than A2 tilde, then we have A1 tilde plus A3 tilde greater than A2 tilde plus A3 tilde. Moving on to formulation of MADM under SVLONN information. And this formulation is made by extending the formulation of MADM, which is available in the literature for single valued trapezoidal neurosophic number and single valued triangular neurosophic number. So I'm skipping all the steps. And we have considered a numerical example in which there are 3 persons, A, B, C, who are applying for a job in a company, and they have different degrees, experiences, and publications. Based upon these 3 attributes, we need to select a best one for the company, and we assume that the weight vector of the 3 attribute is 0.34, 0.33, and 0.33. And the following linguistic terms are also assumed. Based upon these linguistic terms, we have the decision matrix for the attribute C1, C2, and C3. And the next step that we want to do is we need to normalize these decision matrix by using the linear technique for benefit type matrix. And the normalized matrix is obtained in table 2 for C1, C2, and C3 respectively. The next step that we want to do is we need to aggregate the rating values of attributes. And this is done by using the equation SI is equal to summation Wj into Ri j tilde, where summation takes over j is equal to 1 to n. And the corresponding values are shown in table 3. And the next step that we want to do is we need to rank the alternatives. For this, we are going to use the definition of value index and ambiguity index. And the problem is undergone by taking k is equal to 0.4. And we have obtained the value index and ambiguity index of the 3 alternatives A, B, C as given here. In order to rank them, we have considered different values of lambda, mu, and gamma belonging to closed interval 0, 1. And the corresponding results are shown in the table. From this table, we are able to see that B is greater than C, greater than A, and therefore B is the best person for the company. When the same problem is reduced by taking k is equal to 0, then the problem reduces to single value trapezoidal neurosophic numbers. And by using the definition of value index and ambiguity index, we obtain the value index and ambiguity index of 3 alternatives. And for the same values of lambda, mu, and gamma that we used for single valued linear octagonal neurosophic number, we have ranked the same for SV, TR, NN, and we obtain the corresponding ranking. And when we compare these two tables, we are able to see that the ranking that we get in SVLO, NN for different values of lambda, mu, and gamma agree with each other, while the ranking for different values of lambda, mu, and gamma that we used earlier does not agree in case of SVTRNN. And this proposed method can be used for solving the problem of medical diagnosis, pattern recognition, personal selection, and so on. And these are my reference papers. Thank you, sir.
Thank you, ma'am. Any questions? Any questions from the participants? Okay. Thank you, ma'am. Then we will move to the next paper.
Thank you, sir.
The next paper is on solution of an EPQ model via duality principle. I request the participants to concentrate more on the main contributions. So the fundamental rules and the basic principles, if it is possible to skip, you can skip, so that the viewers can have a good idea about your paper. So more time can be spent on the papers instead of rushing. So can I have Anup Khan or Dr. Rasul Kumar Naik? I think they are available.
Sir, am I audible?
Yeah, you are audible. Could you please adjust your mic because it is not clear?
Am I audible, sir? Hello.
Yeah. Now it's better. Please go ahead, sir.
Okay.
The topic is solution of an EPQ model. Yes, sir, please start.
Sir, am I visible?
Yes, your screen is visible.
My name is Anup Khan. I am doing my research under guidance of Dr. Prasan Kumar Nayak, Associate Professor, Department of Mathematics, Midnapur College. My research article is solution of an EPQ model via duality principle. In this article, we use classical EPQ model using game theoretic approach via duality principle. This involves two stages of computation. In first stage, we develop a mode-aware duality problem of the EPQ cost minimization problem with the help of weak and strong duality theory. In second stage, we have formulated an equivalent matrix game problem using Prada's framework. The problem has been solved in two different approaches, namely traditional approach and the other one is game theoretic approach. The numerical illustration shows that a saddle point exists locally, but the global optimality, some duality gap have been found. Finally, sensitivity analysis, graphical illustration, and conclusion are made to justify the novelty of the new approach.
Sorry to interrupt you, Mr.
Sir, I have made. Yes, sir.
So if you're using mic, could you please keep a distance because a lot of grains coming. Audience may not be able to hear properly. Are you using mic?
Okay, sir.
Okay, because
I am using headphone. headphone,
Yeah. Could you please
earphone.
adjust it? Could you please adjust it?
Okay. Am I clear, sir?
Okay. Please continue, please. Sorry for interrupting.
Okay. Thank you, sir. In previous year, the optimum order quantity is calculated via minimizing the total inventory cost and by means of average inventory holding cost and the average fixed cost. And now in present situation, uh, production process is becoming more complicated and it is a part of an intelligent study. So many research are made by several researchers to nano I have studied this literature and I have found that no one are interested in giving the range of total system code. They are optimizing in various way, but they are not giving the range of the total optimum system cost. So duality principle basically works on the theory that gives the lower bound of the minimization problem and the upper bound of the maximization problem. In this way, duality theory gives the range of the cost, and I have used this Preda's framework to develop the game problem, and these two theorems to solve the problem. To develop our model, I have used these notation and these assumptions. And this is the pictorial representation of classical EPQ model and the mathematical representation of the model. Uh, this is the conversion of the classical EPQ model to the game problem using the Paradise framework. This is and the final. This is our main game problem obtained from the classical EPQ model under game framework. We have made this case study in a school company situated in Kolkata, West Bengal. From this data, we have uh, defined some research problem, that is what will be the optimum cycle times so as to minimize the system cost, how much amount of quantity to be produced such that the cycle time cost will be minimum, and what will be the range of total system cost. Now, data obtained from this case study, we have some numerical calculation, assuming that the production rate be 4,000 units, and using our two models, that is traditional approach or classical approach, we have calculated these numerical results, and using game problems, we have found this result. Now we come to the graphical illustration. Here we are presenting the variation of total inventory cost under Cubes and game theoretic approach. Here with total system cost variation around the cycle time 8, that is 0.8 months, that is 24 days. The game model gives better result than traditional approach. Below and above the cycle time 24 days, the system cost began to increase as per traditional approach, but the game approach gives a linear path below traditional approach. This is the variation of total inventory cost along with the time under Cripps and game theory model. Uh, and this is the representation of variation of total inventory cost over time and production quantity under Cripps and game theory approach. We now come to the conclusion. Here we have studied EPQ model under game theoretic approach via Lagrangian duality principle to optimize the cost minimization problem. Basically, for the original problem, we have developed a dual problem using Lagrangian multiplier. Then both the problems have been studied under game theoretical approach. The novelty of this article is that by this approach, we are able to get the minimum and maximum bounds of inventory cost function and ultimately arrive at a conclusion that dual problem is the best fitted approach to solve such type of minimization problem having nonlinear objective function. These are references which I have used in my paper. Thank you.
Thank you, Dr. Anupam Khan. Thank you. Any questions from the participants? Okay, if there is no question, then we will move into the next participant. Thank you, sir.
Okay, thank you, sir.
The next paper is on nanotopology on diminishing fuzzy sets.
Hello, sir. Am I audible?
Yeah, you are
Hello,
audible.
sir. Yes, sir.
Yeah.
I'll share my screen.
Okay. Steve Vasugi is presenting.
Is it visible, sir?
Yeah, it's visible.
Yes, sir.
Yeah, your voice is audible. Please go ahead, please.
Okay, sir. Okay, sir. Good evening, everyone. I'm T. Vasugi, guest faculty, Department of Mathematics, Mother Teresa Women's University, Chennai. My topic is on nanotopology of diminishing fuzzy sets, and co-authors are V. Kamal Nasir, Associate Professor, and N. Chancharani, Associate Professor. Structure of our work goes as follows: abstract introduction, preliminaries, main results, conclusion, future work, and the references. The aim of this paper is to handle the coarseness and uncertainty in the diminishing cells infinite array as it decreases recursively. The vagueness in the diminishing cells infinite array will be taken care by considering it as a fuzzy set at each stage of reduction, and we normalize the pixel gray level intensity values by defining a measure function named as diminishing fuzzy sets DFS. The lack of knowledge in the diminishing fuzzy sets during the compression process of an input image may be handled by nanotopology, which is induced by diminishing fuzzy set with the help of basis, and it also helps to identify the array size with respect to indiscernibility relation in terms of the approximation space and the boundary region. Furthermore, basic propositions, lemma, and theorem for rough topology induced by diminishing fuzzy set are also studied. Fuzzy set theory was introduced by L.A. Zade in 1965 by extending the classical notion of set theory with the grades of membership assigned in the interval 0, 1 and studied properties in terms of fuzziness in a natural way. In 2012, M. Lellis Dibakar et al. Proposed a new topology called rough topology in terms of rough set theory with respect to lower approximation and upper approximation, which play the role of interior and closure of the rough topology, which paves the way to introduce the notion of nanotopology. Moving on to the preliminaries. Let script F be the set of all fuzzy sets such that use a function from R into the closed interval 0, 1 with the following properties. U must be normal, fuzzy, convex, upper semi-continuous, and it should be a compact. And let's see the next definition: approximation space. Let capital U be a non-empty finite set of objects called the universe, and all be an indiscernibility relation. And U is divided into disjoint equivalence classes. Elements belonging to the same equivalence classes are said to be indiscernible with one another. The pair U, R is said to be the approximation space, and you get X is a subset of U, and the lower approximation space of capital X with respect to capital R is defined as LR of X is equal to union over X belongs to capital U, the set of all R of X such that R of X is a subset of capital X. And the upper approximation space is defined as U R of X, which is equal to union over X belongs to capital U, the set of all R of X such that R of X intersection capital X should not be antecedent. And the boundary range again is nothing but the difference between the upper approximation space and the lower approximation space. Moving on to the next definition, let U R be a non-empty finite universe of objects and R be an indissimilarity relation on U. Let capital X is a subset of U and let tau R of X is equal to U empty set L R of X, U R of X and B R of X. Then tau R of X is a topology on U called as the rough topology with respect to capital X. Moving on to the main result, we define a function mu dr from R2 to closed interval 0, 1 by mu dr of X, y, which is equal to 1 when X is equal to y, 1 by n power k when X is not equal to y, and k is nothing but the distance between the points X and Y, where n belongs to the set of all natural numbers and X and Y are the real numbers, and n is greater nor equal to 2. We are going to prove this mu dr is a fuzzy set by satisfying the properties of the fuzzy set. Let us take n is equal to 2. By looking at the definition itself, we come to know that mu dr is nothing but the normal fuzzy set. Next is to prove mu dr is fuzzy convex for any x1, x2 belongs to R2 and lambda belongs to the closed interval 0, 1. Let us take an example as x1 is equal to 4, 5, x2 is equal to 8, 7, and lambda is equal to half. We are going to put this value in the equation 1, and we will be arriving at the answer as 1 is greater nor equal to 1 by 2 pi k irrespective of the value of k. Therefore, mu dr is fuzzy convex for all x1, x2 belongs to R2. And we claim that mu dr is upper semi-continuous when x is equal to y because it attains its maximum value in its neighborhood. And let us consider the subsequence 1 by 2 1 by 2 power 2k of the sequence 1 by 2 power k, which converges to the point 0 as k tends to infinity, which is again contained in the same intervals 0, 1, which satisfies the properties of the fuzzy set. This implies that mu dr satisfies all the properties of the fuzzy set, and we call the set as a diminishing fuzzy set and is denoted by dr. The set of all diminishing fuzzy sets are denoted by the script dr, which may be an enumerable set. Moving on to the proposition 1, a relation RR is an equivalence relation on UR. Here we are taking UR as the universe of array size of the DFS and the relation as the set of all rectangular arrays in a grid, say the pair m, n, where m is the horizontal length and n is the vertical length of the array. When m is equal to n, it is clearly a square array, which is a special case of rectangular array, hence RR is reflexive. Now take m, n belongs to capital RR. Then n, m, which again implies that it is a regular array with the rules of n and m are reversed. Therefore, RR is symmetric. Let me take the rectangular array with m as a horizontal length and n as a vertical length, which belongs to RR, and also we know that m, m belongs to RR. Then it is evident that n, m also belongs to the RR by the symmetry property, hence RR is transitive. And through this equivalence relation, we will have the equivalence class on array sizes of DFS. Moving on to the next proposition, which says that the pair RR is an approximation space. We prove this with the help of the previous proposition and the approximation space definition, and also by considering the subset XR of the universe of discourse UR. Eventually, we would arrive at the lower approximation space and upper approximation space, as well as the boundary region for the array size of the diminishing fuzzy set. Next, we will be seeing the lemma. The triple UR, tau RR, XR is a rough topology induced by a DFS. We will be seeing the lemma. We will have the help of the previous propositions 1 and 2, and we would get the topology as the universal set, empty set, the upper approximation space, lower approximation space, as well as the boundary region as it is induced by DFS. In the above rough topology for DFS, we had at most 5 elements in the collection tau RR. Hence, we call this collection of elements as nano topology because it has only 5 elements. induced by DFS and also called as the nano diminishing topological space NDTS. It is denoted by UR, the pair UR tau RR. The elements of nano diminishing topology is also called as nano diminishing open sets and its complement as nano diminishing closed sets. Next, we will be seeing the theorem. Script BRR forms a basis for NDTS, that is nano diminishing topological space. We prove this by satisfying every open set is a union of sets in this class or collection, as well as the element. If the element belongs to the intersection of the two basis elements, then there is an element, say BR, which is again which contains the element of X, such that the basis element BR is contained in the intersection of the basis element, also with the help of the lemma which is explained earlier. Hence, we would witness the collection script BRR contains the universe of discourse, local approximation space, and the boundary regions forms a basis for NTDS. NTDS defined by the script BRR may handle the lack of knowledge and coarseness of diminishing fuzzy sets during the image analysis phenomena. So, in this paper, the basic properties and the propositions are extended for diminishing fuzzy sets with respect to indiscernibility relation on the array size in a grid, and the basis for the nanotopological space induced by DFS is also studied. Our future work aims to overcome the coarseness and also to recognize the similar size and area of the array while compressing the input image. These are my references. Any questions, sir?
Any questions from the participants? Thank you, ma'am. So, have done a very wonderful job.
Thank you so much, sir. Can I stop sharing, sir?
Yeah, you can stop sharing. Thank you.
Okay, sir. Thank you so much. Bye, sir.
The next paper is there is no paper like 107.
Sir, it is 117, sir.
117. Okay, fine.
Divergence measure for.
Yeah, the next paper is on a divergence measure for intuitionistic fuzzy matrix. I think the author Alka Jain and Preeti Gupta are presenting. Are you there?
Whoever is joined in the name Galaxy M21, can you unmute and speak? May I know who is this?
Yes, I have unmuted.
Okay, you are?
Yeah. Oh.
Yes, good evening to all of you.
No, your name, ma'am?
Alka Rani. Alka Rani.
Are you presenting?
Alka Jain. Yes, I am presenting my paper divergence measure for instantaneous fuzzy matrices.
Okay, ma'am. Just a minute. I'll change you to the panelist. You can share your screen now. We can start presenting.
Okay, sir.
Are you able to share? Yeah, it's coming.
Yes. Is my screen presenting on your screen? Okay. My paper title is Divergence Measure for Instinctive Fuzzy Matrix under the supervision of Hatak. This paper introduced a new divergence measure for instinctive fuzzy matrix with the proof of its validity, multi-criteria decision-making problem as well as multi-attribute decision-making problem. Finally, the application of this instinctive fuzzy divergence measure is applied on numerical example. In recent times, due to increasing complexity of socio-economic environment, instrumentistic fuzzy sets are more eminent than the fuzzy sets in maintaining the ambiguity and exaggeration of real-life problems. Divergence measure is a significant tool for evaluating the amount of discrimination. Shannon 1948 defined entropy measure for probability distribution. Kullback and Labler firstly investigated divergence measure which assumed probability distribution deviates from the original one, found applications in many studies. Atanasoff proposed a generalization of fuzzy set. An instinctive fuzzy set is characterized by two functions expressing the degree of membership, non-membership, and a hesitation index. Instinctive fuzzy measures are more appropriate in decision making. We can see these references. Mishra et al. Provides me direction to propose this work. They proposed an instinctive fuzzy divergence measure based on electric method for the performance of cellular mobile telephones. Inspired by above mentioned work, we propose a divergence measure for instinctive fuzzy matrix for applying in multi-criteria decision making in every field of real world like a medical, engineering, business, where decisions have to be taken on the daily basis. Instinctive fuzzy set. In 1986, Atanase gave the definition of instinctive fuzzy set. Here, let taking U be the universe of discourse. Here, U1, U2, Un be the elements of the set. Then, and IFSG on U is defined as U1, UI, mu I, mu G, mu VG. Mu G stands for membership degree and VG stands for non-membership degree. Both are belonging the range 0 to 1. Here the instinctive index also there, which can be calculated by the formula 1 minus mu G minus Vg. After this, the definition of instinctive fuzzy matrix is this. Let taking A is the fuzzy matrix, instinctive fuzzy matrix. Here Aij mu is the membership value and Aij V is the non-membership value. We can define an IFM as mu11 V11 is the first element of the matrix and mu Mn Vmn is the last element of the matrix. Some existing divergence measures are given here. Deluca and Termini give a divergence measure. 1989 में Pal and Pal have given us exponential entropy measure. After that, divergence measures are given by Jansen and Shannon and many more. Properties of a divergence measure for instinctive fuzzy set. If any divergence measure is applied to instinctive fuzzy set, it must have four properties to be hold. DAB is equal to DBA, DAB is equal to 0 if A is equal to B, DA intersection C, B intersection C less than DAB, and D union C, A union C, B union C always less than DAB. Here we propose a divergence measure for instinctive fuzzy matrix minus 1 by Mn summation mu A xy plus mu B Vij by 2 log mu A Xij plus mu Byij. Here A and B are the two matrices. Mu A Xij is the element of A matrix and Yij is the element of B matrix. Properties of the proposed divergence measure for IFM. We have propose the divergence measure and satisfy all the properties by this measure. DAB is equal to DBA. And we have proved these properties in the form of theorems, but I have skipped the proof of the theorems, and I am proposing the application in decision making and data reduction. The proposed measure have various application here. I have taken the real life data. The Department of Statistics, Maharshi Dayanand University, Rohtak has a problem. What software should be introduced for the students for the students of the department. So I have collected some data from teachers and outside about the software. The data is collected by interview method, and I have taken instantistic fuzzy values. There are 6 softwares I have choose: SPSS, C++, R, MATLAB, C language, from which only one is included in the syllabus. I have chosen 6 parameters. They are job efficiency, first one, latest, useful, in statistics, cheap, easy to learn, and curriculum related. These are the 6 subsets about software S1. The parameters mu1 value is 0.1 and v1 is 0.2. Taking this data, I have making a table about software regarding parameters. After this, matrix representation of the table becomes this. I have taken the preference order of head of the department. They give me preference to the parameters as parameter P1 taking value 0.8, 0.1. Similarly, parameter 2 taking value 0.6 to 0.3. Then an instantistic fuzzy row matrix can be represented as the preferences of the software. Now divide the above fuzzy matrix into the 6 row matrices and calculate the value of calculate the divergence measure between row and column matrix. I have taken S1, S2, S3, S4, S5, S6, 6 row matrices and 1 column matrix T, and comparing this divergence, I have find minimum is S3. Third row matrix has minimum divergence. So I can say that S3 will be the best preference in other softwares. Now I am reducting the parameters which are not useful in the study. Taking the preferences of parameters from the head of the department, I have making a column matrix 0.8, 0.1 the parameter values, and take features value, and finding the divergence between the parameters of S matrix and Y matrix. The minimum value of the divergence is 0.158482, which is for matrix F1 as compared to other column matrix. So F1 is a less optimal solution for F1. So parameter is more significant other than. So F1 cannot be removed. So we find difference between S1, S2, S3, S4, S5, S6 and Y matrix. We can see here the difference of V1 is 0.33625. The optimality of the decision is not maintained after removing the feature 1. When we remove F5, the optimality is maintained, so we can remove this because our decision is not changed. These are calculated values in the software. I have checked where the decision is maintained or not. Here we can see from the results only F2 and F5 parameters should be removed. We can eliminate the following parameter subset: F2 or F5 or F2 and F5 both. The chapter I am coming to the conclusion. The chapter introduced logarithmic divergence measure for instantistic fuzzy matrix. Proposed measure is a valid measure as it satisfies all the axioms. Properties in the form of theorems are also proved of the measure. An application of the measure is presented in decision making problem and parameter reduction problem. We may eclectic the best alternative in preference to other available alternatives in decision making problem. We remove those features which have inconsequential to make decision, and after eviction of those features, decision is maintained in feature selection problem. These are some bibliography I have used in my paper. Thank you, sir. Is there any questions?
Thank you, ma'am. Is there any question from the participants?
Sir, there is a question from in the Q&A box, sir. Ma'am, can you answer
There
that?
is a question from the participants.
Yes, yes.
What is the difference between a distance measure and a divergence measure? So that is a question from the participant.
Yes.
Can you take up that?
Please repeat the question, please.
What is the difference between?
Hello.
Are you able to hear me?
What is the difference
What
between?
is the difference between a distance measure and a divergence measure?
I have not read about the distinction measure. I have read about divergence measure, similarity measures, and distance measures. I have not read about this.
That's what the question is. Can you differentiate what is the difference between this distance measure and divergence measure? How you are differentiating these two things?
सर डिस्टिंक्शन मेजर के बारे में मैंने कुछ नहीं पढ़ा है अभी तक. Yes, sir. I have read about divergence measure, similarity measure, and distance measure. The term distinction measure I have not read till now.
Ma'am, the question is in the Q&A, ma'am. Can you click
Is
and
there any?
check that?
Okay. Where should I check?
In the Q&A box,
In the
ma'am.
Q&A box, it was sent to you.
Where should I check?
Ma'am, can you click on your screen? There is one Q&A on the
Okay.
top.
Yes. What is the difference between? Yes. I can explain. I can explain distance measure and a divergence measure. Differentiate between what the properties they do not follow about them. Distance measure means what the distance they are closely related or not related, like correlation measure ना. कोरिलेशन मेजर में हम जैसे दोनों में डिग्री फाइंड आउट करते हैं, उसी तरह से डिस्टेंस मेजर में भी हम क्या फाइंड आउट करना चाहते हैं कि वो दोनों कितने क्लोज हैं. Distance measure is different thing and divergence means differentiate between two measures. I think I have taken two matrices. I have to find what the difference between them. Distance measure find what the correlation between them.
Mr. Abdul, I think you got clear, right? What she means to say is distance measure is the distance between the populations. And
sets to population
yeah, it's a two
objects.
set of data. Okay, whereas the
yes,
whereas the measure just divergence measure will give you the distance between the measures.
Differentiate two objects. Differentiate two. What's the difference between two objects?
Okay. Thank you, ma'am.
Okay, sir. Is there any questions?
Any other questions? Okay, that's the last presentation of this session. Over to the conference team.
Thank you, sir.
Madam,
Yes,
thank
sir.
you.
Thank you. Thank you for chairing this session, sir.
Thank you for offering me this, and it's really a wonderful opportunity for me to go through all these papers. I really appreciate the participants for taking so much of interest, and for the conference committee also, I thank them for giving me this opportunity. A variety of papers they have chosen from various parts of the country. Please continue. Thank you for giving me this opportunity.
Thank you, sir.
Thank you, sir.
So with this, we come to the end of the symposium on fuzzy set theory and applications. Thank you to all the participants. Thank you. So I will now close the meeting.